I will do it. Okay, so good afternoon, everyone. Here is our geoscientist from Petronas, Mr. Jairo, and he has almost 20 years of working experience with, um, exploration related projects in the oil and gas industry. Working in many of the data types in the oil and gas industry, and involved in a number of projects, and also published a number of papers, and also has delivered a number of courses to postgraduates, and as well uh, as adjunct lecturer to undergraduates as well. Without further delay, I would like to invite you, but just this is a brief introduction. So if you wish to add a little bit of about yourself, you are most welcome. So the floor is yours, Jairo.
Okay, Haile, thank you. Good afternoon, everyone, and thank you again for the invitation and you guys for being here today. Again, just to give some details more about my CV. I've been working around the oil and gas industry for a bit more than 20 years, 25, 27 years around. And out of this time, I've been doing reservoir modeling for about 20 years already. So I got experience around the world. I'm originally from Colombia. I started working there. I'd done projects in Venezuela, in Argentina, in Brazil, in Mexico, here in Malaysia. Of course, when I joined, I had the opportunity to see projects in Vietnam, in Indonesia, and some areas in the UK. So I'm very lucky, to be honest with you guys. I've been involved in the oil and gas industry, as I said, so long. So I've seen a couple of crashes of the oil price. Now it's getting better. So I welcome you guys to be today with me. And the idea is in this 2 hours session, I will give you a lecture about reservoir modeling. I will be touching also something about reservoir characterization for you to get familiar into that. And I hope you enjoy. So feel free to ask me any question. If you have test something in the chat, unfortunately, I cannot see the chat during the presentation mode, but I hope any one of you guys can interrupt me rather than just testing the chat. I prefer you to just interrupt me and ask me the questions. Okay, so this is going to be 2 hour sessions. We will have a short break, probably 5 minutes break once we finish the first hour, and then we will continue on that. All right, welcome again. So the idea today is I will show you 5 topics, and basically I will start with the basic definition, and then I will take you through the whole process of how we create a reservoir modeling, and at the end I will also be talking about sensitivity and uncertainty analysis, which is one of the biggest steps that we do when we are doing a reservoir model. Okay, so let's start with basic definitions. And first of all, let's try to agree on what could be a good definition of what is a 3D model, right? One of the best way to define 3D model is mathematical. I think could be maybe someone is on the okay. So basically, the definition is a mathematical representation of what? Of a reservoir, right? Of whatever we see below the surface, where we have an accumulation of hydrocarbon. And the idea is that we need this representation for many reasons. We will see some of those reasons. One of them is you naturally can imagine that if you have this representation, you could have a common language to talk for all the disciplines. So the geologists, the petrophysicists, the reservoir engineers, the geophysicists, the managers, all of them can talk in the same language once we have standardized a 3D model, the geology in a 3D model. And then, of course, we can calculate volumes and we can make simulations and make predictions of what could happen if you drill certain wells, if you inject certain fluids, what could be at the end, what is the recoverable that we can extract, the amount of oil or gas that we can extract from that reservoir. Now, in this cartoon, what you see is a real sample in a field here in Malaysia. you can see different colors, right? And you more or less can see a 3D shape where you see kind of a container, and the colors are representing the faces. So what you can see is a transitional environment between a short face environment, where the aperture face could be located in the bluish area. And whenever you go to the distals, which is in the left side of the cartoon, you're going to a bit more distal. So we can capture that kind of geology, and then having that geology into numbers will allow us later to predict many things when we are doing development, all right? So let's look at a very high level workflow that we normally use to build a static model. So first of all, we start with the interpretation at the well location. So you have drill wells, you have certain wells, and in that way, in those wells, you normally acquire data like wireline logs, core data, for example. And then using that information, the first thing that we try to see is what kind of lithology, what kind of facies, what we call facies, what kind of lithology we have in that particular reservoir, right? And then, of course, we have a description, which is a qualitative description coming from the core, but we need to quantify that. We need to assign numbers to that quantitative description. So at the end, we need to create a quantitative log that we call facies at the well location. That's kind of one of the first steps when we are doing reservoir characterization to get this input data inside the model. Now, once you have these facies descriptions at the core level, when you have a well with core, so basically the idea is that we try to create a mathematical model to try to predict all those facies that you have seen in the core away from the core interval. So let's say you have taken a core only in this yellow sand here, right? So you have the description here, and now the target is how you can propagate in the whole well trajectory that kind of description. And for doing that, you need to create a mathematical model to try to propagate away from that core interval, so you can have a full new log interpreted called, let's say, facies, right? Now, in parallel, normally we have a team. This is done in a team, and in parallel, that you could have geophysicists working in the seismic, right? And I guess you guys are familiar with what is seismic. And the idea is that the geophysicists, they take the well tops, which is basically the top of the reservoir or the zonation inside the reservoir. And having those well tops, they tie this information to the seismic, which is acquired mainly in time. So they made the interpretation of this seismic, they propagate away from the well location, that particular marker, they made the interpretation, what we call it peaking interpretation. And then using that interpretation, they can create a map, right? A 3D map of, let's say, the top of the reservoir, or even the base of the reservoir. And also at the same time, when they are peaking, they try to describe this kind of discontinuities that we call faults. So, you know, due to tectonic, the rock can be failure, and then there are some faults right there. So they also interpret not only they don't only pick the surface, the map, but also they pick the fault inside that particular reservoir. And then having these constraints, let's say the maps plus the faults, then we can create what we call the framework or the container, which is basically at this stage. Having that container, so it could be a parallel work actually. The geoscientists and the sedimentologists could start working in what we call the concept. We need to create a concept before you propagate any property inside your container. And what is the concept? The concept is basically a geological model, a geological picture on how the geologists of the field, they imagine, how they imagine the facies to be distributed, right? So over there, they take the interpretation from the core and they say, okay, perhaps we are in a shallow marine environment. So we are expecting to see bars, we're expecting to see channels. You have a continental environment and things like that. So that's kind of the thing that we call the concept, creating a concept. And of course, that concept is not just simply a qualitative description, but also you need to represent that concept into a quantitative description, which is basically what we create maps, right? Trend maps or things like that. And of course, the seismic interpretation, sometimes we have quantitative interpretation, inversion studies, etc., coming from the seismic. They support also the creation of that kind of cartoon. Having that information with the wells, etc., what we do is we try to first of all capture inside the container what we call the depot fishes, right? And the depot fishes is not a thing like a large scale bodies, geological bodies that we imagine we have inside the reservoir, right? So you could imagine a channel, for example, just a single channel. Inside that channel, you're not expecting to see only one single lithology, right? So then the channel itself, the channel belt itself, is that what we call the depot fishes. And after you capture that, we can model inside that particular body, let's say the channel, you can model what we call the lithofishes, which is the next step. So internally, we divide the channel into more clusters or groups of fishes inside that particular channel. And having that, of course, we can use that to constrain the modeling of the rock types, porosity, permeability, saturation, etc. So all the petrophysical properties that we are going to populate inside, they are constrained to the previous concept that you have created before on the previous steps. Now, knowing that there are a lot of things that are uncertain, so you imagine having a field of, let's say, 10 kilometers width, and let's say 3 kilometers, let's say 3 kilometers width, and the length, let's say 10 kilometers. And then imagine that, picture that dimension in your brain, right? And now imagine that you have some few wells, let's say 5 wells. So one well could be separated apart, let's say a couple of kilometers. So in between those wells, there are a lot of information that we don't have, and this could create a lot of uncertainty. We don't know, right? There are a lot of uncertainty. Therefore, we cannot create just one single model. The idea is that we need to create multiple realizations, multiple kind of models, if you wish, of that particular reservoir. And therefore, in the process of creating those multiple realizations, we have the statistics approach to help us to quantify the level of uncertainty that we have. So therefore, at the end of the study, you will be able not only to produce multiple realizations of the models, but also you could select, let's say, according to the percentiles, you can select what could be your P10, your P50, and your P90 model to be provided to the reservoir engineer. And then having those particular 3 models, the engineers will start running fluid simulation to try to understand how the hydrocarbons and the water behave once you start injecting or producing in your field. Okay, so basically it's kind of a loop. It's kind of a loop where sometimes you drill new wells, so you need to go back and update your models. Sometimes when you drill a new well, it could happen that you found that there are different EODs or depositional environments. Therefore, you need to change the model, you need to rebuild it, etc. So this is a very active process. So don't believe that we build just a model and this model will stand until the end of the life of the field. So it will change, it will evolve once you start acquiring data, and therefore you will be updating the model. Okay, so this is basically the big picture, and we will be talking on all those steps today. Okay, so that's the idea, that we will be ending with the uncertainty and sensitivity analysis. Okay, so let's start with this part, which is the framework that I told you is something that can be happening in parallel while the geologists are creating the concept and working in the core and so forth, and the petrophysicist is doing the petrophysical interpretation. At the same time, the geophysicists can be working on the maps, creating the maps, right? And this is basically, in this part is where we can create the framework.
I have a question here.
Yeah, please go ahead.
May I interrupt? Sorry to interrupt you. There is no chat option. Otherwise, I would have asked that question over the chat. Just a quick, if you could go to the previous slide. If I wish to integrate rock physics in this workflow, could you just quickly comment where exactly and how can I integrate rock physics in this workflow? Thank you.
Yeah, good. Thank you. Good question. So there are different steps where you can do so, right? In the first step depends on what kind of, let's say, like I would call it in general QI studies, right? Any quantitative inversion or whatever you have. So you could depends on what you can see. So sometimes the seismic is good enough, and you can start creating, let's say, geobodies. So you can start extracting those geobodies, and you can pass them in this stage here when we are creating the concept, right? Additionally to that, let's say you have a a very nice seismic, and you end up having a very nice correlation between the acoustic impedance and porosity, and you can provide a 3D cube of porosity or acoustic impedance. So then that can be integrated over here during the porosity modeling, for example. That can be also done. Sometimes you are able also to create some net to gross maps, and they are very useful in turbidite system, for example. And those are basically coming, could be here in the lithophases or even here created in the concept. Okay, so there are many areas where you can integrate whatever outcome from your quantitative interpretation. Did that answer your question?
Yeah, thank you. Yes.
Okay. Okay, so coming back to the container, so you need to create what we call a structural model, right? And there are two basic components of the container. And the first one is the structural interpretation itself, and the second component could be the stratigraphic interpretation, right? And in the structural interpretation, so as I mentioned before, you can extract your horizons, which are the maps, the tops and the bottom, and the faults, of course, associated to all those discontinuities in the field. And then, of course, you can also create your isocores, which are thicknesses in across the zonation that you would like to create in your reservoir. The next step is, of course, if there is a possibility and the seismic allow you to do, you should do a stratigraphic interpretation as well. So in the stratigraphic interpretation, you would support the well correlation. So you would say, okay, according to the seismic, which sometimes we assume then to be timelines, you could support them with during the correlation of the wells. Then you need to do the zonations. And then this is very important. This step, which is the layering scheme, we need to decide, let's say you define a reservoir between the top and the bottom, but the internal layering or the strata, you have been in field trips, you will see how the strata itself, it behave in a package, right? So internally, you will have a lot of call it geometries or layering inside any package. So in the seismic can help you to see you have a proportional layering, or you could have an erosion at the top, so you can follow the base going up to the top, and all the layers will be truncating at the top, or you could have an erosion at the base, so the top is going to be conformable, and then you will be eroding at the bottom. So that kind of the structure or that kind of a layering scheme is going to help you to discretize vertically your reservoir or your zones into minor strata, if you wish. Okay, just in a moment we will see some examples. Perhaps you will understand this further. So having this, so then you can create your container. This is a small animation. One of the projects in Vietnam is a carbonate reservoir, where I basically have created a container, and I captured this kind of animation step by step, so you will understand how I created this container itself. So what you see there in colors is a depth map. Wherever you see reddish is a shallow part of the reservoir, and whatever is bluish and kind of purple colors, you will see deeper into the structure. And then the points, we have 2 points at that time, two wells, basically here and here. And then what you see with these lines is what we call the fault sticks. And the fault sticks is basically a polygon. Each of these fault sticks is a polygon where, let's say, the geophysicist display an inline or cross line section, seismic section, and he see a fault. So he pick a polygon where the fault is. So that polygon is translated into the software into what we call one fault stick. So then he moved to another cross line or inline, keep interpreting the same fault. So another fault stick will be interpreted, and at the end you will have a set of polygons representing kind of a discretization of that fault plane. And those fault sticks are used in the model. So, and those are the lines that you can see over there. So in this particular case, the first thing you need to do is ensure you have an area of interest. You need to define your area of interest. And one of the best way to define the area of interest is, first of all, you need to take into account the boundaries. For example, you're working in a joint ventures and you have only the rights to exploit a particular block. So then you need to honor that kind of boundary. And the second thing that you need to take into account when you're creating your area of interest is your pay area. And how you do the pay area, basically you have your structure, right? Your structure map, and then you put the contact, and this is basically the blue color that you see on top. and then you can see where the hydrocarbon is sitting. So you can define that as your area of interest. So when you're creating a model, you have to ensure that your area of interest is properly set. And the reason why is because if you miss one area, let's say you decided to build only this small part here of the structure, and you miss the other part without intention, and you build your model, let's say you spend 3, 4, 5, 6 months building your model, and then you realize that your area of interest was screwed, that you didn't really cover the whole pay area. You need to rebuild the whole thing from scratch. That could take you not the 6 months, but it could tell you sometimes that you don't want that to happen. So the area of interest is a very important step that you need to consider before you start embarking. And more than an area of interest, I would say it's a volume of interest. So then you need to also investigate how many reservoirs vertically you would like to include in that particular model, right? You would like to include the minor reservoirs and the major reservoirs, or you would like to model only the major reservoir, etc., etc. So you need to make an agreement in your team, including your reservoir engineer and of course your manager, whereby you will decide, okay, we will be modeling only the major reservoirs and the minor reservoirs won't be modeled, for example. So then you don't include it in your model. Okay, that's kind of the volume of interest. Then after that, what we do is we translate the fault sticks, which is the polygons that I described before when the geophysicist is picking the fault, right? Those fault sticks can be converted, transformed into fault planes, and those are the fault planes that you see in the view. And having those, then you can do a QC. Basically, you can start QCing how the faults looks like against your fault sticks. So the idea is that you would like to capture as close as possible your input data. Then this is not really required like creating points, but I really prefer when I creating a structural container, I prefer to translate everything to points because that would allow me to edit certain areas when some anomalies are happening during the model. Okay, so but this surface to point is not really required. You can directly work with your maps. Okay, and then the idea is that having the surfaces, you translate those surfaces in what we call horizons. Okay, so it's kind of a transformation of a regular surface into a non-regular surface in the software. Okay, so then basically that's it. You're ready. You have cut. You see the initial map. It was having the surface was continuous everywhere, but now once you have created the horizons constrained to the faults, you can see the fault throw. You can see the cut that the fault has created. In this particular case is the normal fault, so you can see a gap in between the surface here and there. Okay, and having that, of course, you just simply do a QC, and if you need to change something, for example, you could even go back. If you have found, let's say, one of the faults is not consistent with whatever you have modeled, and you have any equation, for example, on the truncation of the fault, if this fault is truncating this fault or they are not touching, which are very important questions for you to answer, right? Because if these two faults are touching, you could be creating two compartments into the two fault blocks, right? But if the faults are open, the fluid can still be communicating. So therefore, one of the things that we do is we iterate the fault modeling with the geophysicists, and we go back and forth. We go to the geophysicists and say, hey, listen, I see this fault very close to this. Should I truncate this or they are really open or not? So then you work on that kind of in a loop until you more or less you get your structure properly done. Okay. Now, once the structure has been created, once the container has been created, so then you have something to start populating inside, right? You have your framework. And before we go into the details on how we populate the container, it's important for you to understand what kind of properties we need to model and why. And for doing that, you will need to understand properly the equation of the hydrocarbon in place. So in the hydrocarbon in place, first of all, the first volume that you would calculate is what we call the gross rock volume, GRV, right? And what is the GRV? The GRV is basically, you have the structure map, let's say this one, and then let's say you have a contact somewhere here. So your gross rock volume is going to be everything which is above that particular contact, right? And when I said everything is, you imagine having a massive object in there. So at the moment you are not thinking about that object is containing porous or porosity, right? You are not, you are imagining just a solid kind of rock right there. That's what we call the gross rock volume. So it depends on what? Depends on the structure map and depends on your contact. So everything above that contact and constraint to the structure map is that we call the gross rock volume, okay? And then, of course, as you know, inside that particular piece of rock, you could contain certain lithologies that they cannot contain, or they are not containing enough amount of resources. For example, let's say the shales, until probably 10 years ago, we used to believe that the shales cannot produce anything. So then what we used to do is what we just simply, using petrophysical evaluations, we define what is reservoir and what is non-reservoir. So out of the whole container that we already created and say, okay, above the contact, out of all these containers, there are certain rocks, there are certain lithologies that we don't consider like reservoir. They cannot contain hydrocarbon. So then you need to extract that particular piece of rock so you don't overestimate the volume. One of the final goals is to create volumes, right? How much volume you have there. So then you need to know which rocks cannot contain hydrocarbons so you can extract them out of that particular container. And one of the ways to do this is through what we call the net to gross. So you need to take the net gross, the gross rock volume, then you multiply that times to the net to gross, or you extract the rock that cannot contain hydrocarbon, the non-reservoir, and then you can calculate what we call the net rock volume. So you can see here is the gross rock volume times the net to gross, you can have the net rock volume, okay? But then imagine that now about the contact, now you identify certain rock that can contain hydrocarbon, right? But out of that, still, you know that the rock is not fully massive, solid, but you know that you have certain porous, right? And inside that, those porous, like the porous that we have in the skin, inside those porous is where the hydrocarbon and the water also can be trapped, can be contained inside that, right? So therefore, you cannot say that the whole rock is full of water, or full of gas, or full of oil, right? You need to discount certain grains, the rock contains grains, particles, right, that need to be discounted from your calculation. So therefore, in that sense, you will need to calculate what is the porosity, and by definition, you know, the porosity is the empty space divided by the total volume, right? This is the definition of porosity. So therefore, you multiply that net rock volume that you have before times porosity, and you will have what we call the net pore volume, okay? Now, you are now at the porous level, right? You already discounted. You already discounted the grains. Now you are at the pore. But inside that pore, you look at more in detail. That pore can contain different fluids. It can contain, for example, oil and water, right? And that water could be irreducible water, right? It's the small amount of water that is surrounding the grains, for example. So therefore, you need to discount that kind of water. You are trying to calculate the amount of oil, because if you don't do that, then you will be overestimating the volume, right? So therefore, the next step is you need to take your net pore volume and you need to multiply that times to your hydrocarbon saturation to produce what we call the hydrocarbon pore volume, okay? And now the hydrocarbon pore volume, now you are already at the fluid level, you know, okay, this is how much hydrocarbon I have, how much gas or how much oil or how much of both, right? So now, but this is at the reservoir conditions. So you imagine the reservoir being deep, let's say 1 kilometer, for example, deep, right? So the amount of pressure that you have right there will make that the fluid is, of course, is compressed, right? There's a lot of pressure. So then when you produce, you drill a well and you touch the fluid at that depth, he will start, of course, due to that high pressure, the fluid will try to move from high pressure to low pressure, right? And lower pressure would be in the surface. So the fluid automatically, if he's in enough pressure, so he will start flowing to the tube and so to the well outside. And then once he reach outside, what's going to happen is if you have oil liquid, right, it will tend to start making the gas to be free. So due to that process of gas liberation during the change in pressure between the reservoir and the surface, so what's going to happen is your amount of oil will be shrink, right? Because now the light components will be escaping the fluid, and then the amount of volume at the surface will be different than the amount of volume that you have at the reservoir, right? So therefore, we need to integrate what we call the formation volumetric factor, which is kind of a parameter which will allow us to make that correction due to the change in pressure in the reservoir conditions and surface. Okay, so then you need to use the formation volumetric factor to really calculate what we call the stock tank oil in place or the gas in place, which is basically how much of that can be at the surface conditions, right? When you use the formation volumetric factor. Okay, so knowing this theory, which I think you guys were familiar on this before, now I want you to appreciate what are we going to do with the model. So the intention is first try to see the gross rock volume, then see how we capture the net volume, the net pore volume, and the hydrocarbon pore volume to get the volumetrics, okay? Now, when do we need to build a model? So as you know, a field is having different stages. So the first stage, for example, could be what we call the exploration stage, which is not in this cartoon. So in the exploration stage, basically what we are trying to do is we are trying to find the hydrocarbons, right? And then once you drill a well, for example, you have discovered, the next stage could be what we call the appraisal. So just because you drill a well and you know you have hydrocarbon right there, you cannot just simply start developing, right? You need to investigate and see how big, how much really you have. And this at that stage is what we call appraisal. So reservoir modeling sometimes it's not really frequent to happen, but sometimes we, during the appraisal stage or even the development or even in the exploration stage, we can build models sometimes. But the most preferred method at those levels are basically calculating using 2D maps. So you have only maps and you can do calculation using maps. This is what the explorationists, they do, okay? But the real fun with reservoir model starts once we start doing the development, the development phase. So now we know more or less how much hydrocarbon we have. So we say, okay, this is economic. So we can start drilling, we can start producing, we can start injecting, etc. So during development is basically where we can start creating models. This is basically what we call the field development plan, where we already are going to embark into the development. We need to create a model for many reasons, as I mentioned. You need to more accurately calculate the volumes, and also you will need to have a platform for you to run simulation of the fluid, how the fluid will move through the porous media, and you will need to extract predictions at the end, right? So we don't want to start injecting, for example, water without knowing if that amount of money that we will be putting upfront for the injection cannot be paid back due to production, right? So then before we embark into any project, we do simulations and we predict. We go and we say, okay, the most likely case is that we can recover this amount of hydrocarbon, or the worst case scenario is this amount of hydrocarbon, and the upside or the best case would be this amount of hydrocarbon. So then we make the decisions, we run economics, and based on those numbers, we say, okay, yes, we can do that. We can do this first pilot, for example, etc., etc. So that's where the real story is happening for reservoir model, right there when we are doing field development planning. Okay. Any questions so far before we go to the geostatistical algorithms? These are basic definitions. Remember, we are just starting warming up. Okay. Okay, so let's have a tour around the statistical algorithms that we use in reservoir modeling and characterization. So what are really the pros and the cons of geostatistics? By the way, in the oil and gas industry, geostatistics is the method that we use the most to create reservoir models, right? Even when we are creating a map. So imagine the geophysicists, when they go and interpret, they display the line and they pick the top of the reservoir, for example. Then when they move to another line, so there is a distance, right? Could be 50 meters, could be 10 meters, depending on, you have a 3D seismic, could be 10 meters, for example. But at the end, there is a gap in between. So in between those picking, you will need to create data, right? Let's say interpolate data in that case. Or sometimes you need to extrapolate data. So even for those kind of processes, you will need to have geostatistics. Okay, and basically your statistics, as the name say, statistics applies in your science. So what are the pros? What are the cons and the pros? Well, your statistics does not replace, this is very important, does not replace or reduce the need of good data. That's a misconception sometimes. Some people, they said, well, you can, since you can create a porosity model, why do we need to acquire core data? Yeah. Your statistic will allow you to create a porosity model. But at the end, you know that you are uncertain what you are doing, right? So at the end, your statistic is not intended to replace or reduce the need for data. Right? Of course, this is very positive for the geologists. The statistics will never also eliminate the interpretation. So meaning to say the geologists will always need to. Okay, so that's a good thing. So we will have a job to be done still. And also, your statistic does not substitute the lack of, let's say, knowledge in geology, right? So if you don't know what you're doing, you can create a model, right? But that model could not be valid. And if the model is not really valid, and then you try to make predictions, you can, misguide management on economical decisions that can be really costly for the company, okay? But the good thing is that the statistic will allow us to create multiple models. Imagine yourself having two sedimentologies. It happens to me before. Imagine yourself having two sedimentologists, and one sedimentologist believes that we have a tidal influence, for example, and the other sedimentologist say, no, I don't see that tidal influence. I not agree with you, and they disagree, right? So at the end, you could see two models. One from sedimentologist A, one from sedimentologist B. And still the statistics will allow you to capture those two models in a time manner, so in a time frame. So it's not impossible to create 2, 3, 4 scenarios and then use them to see what is the implication of having, for example, a tidal influence in the model or a non-tidal influence in the model. What is the implication of that? That's the beauty of statistics. Additional to that, we'll maximize the use of the data. And the reason why it's maximized is because now we have found a method to integrate data coming from different sources. Okay, so now before, the people, when I say before, it's probably 30 years ago, the people, they used to work in silos, like in islands. So one guy working there, the guy separate, and so forth. Now with this statistic, you can maximize the use of all that data because you can integrate everything in one single model or multiple models, right? And very important is it helps us to quantify the uncertainty, because one of the things that we are sure and we are certain is that we are uncertain. And the reason why we are mainly uncertain is because mainly the lack of information. There are other sources of uncertainty, like the tools and so forth, right? The sensitivity on the tools and so forth. But the main one is the lack of information. That's kind of the issue. Okay, why do we need your statistics? Okay, first of all, as I told you before, help us to put geology, that used to be a very descriptive branch science, into numbers. Now we become more quantitative, so it's very nice. Now, it helps us to capture the constraints. What is a constraint? For example, capturing the map, top and base, capturing the presence of faults. That's kind of the thing that we call constraints, right? Or for example, a EOD, or environment of deposition. That will also is a kind of a constraint. You know, a channel is running here, is constrained in these dimensions, and that's something that your statistic will allow to do. Now, of course, help us to capture the depositional model. As I said, it helps us to generate realistic models and properties. Of course, at the end, we need to have the properties of the model to quantify the volumes and make predictions. The data is having distribution. So what are the distributions? So let's say some data behave like Gaussian distribution, like porosity. Some data can behave, let's say, log normal distribution, like permeability. So your statistic will reproduce those kind of distributions. So it's kind of a signature of the data, and the statistic will allow you to reproduce that into your model. We already talked about the volume, how much we can have. They can help us also to say where these volumes are placed, right? So you could say I have 50 million of Stockton barrels, but you could have 50 million in one single pocket, say, easy to be drained, or you could have the 50 million separated into small bars in the geological, let's say, shallow marine environment. So it's going to be, you will need more wells to be drilled, right? So then with your statistic, we'll more or less pinpoint where that hydrocarbon is placed. Okay, what else we can do with statistics? Sorry. It will tell us what is the rate of to be successful or unsuccessful when we are drilling wells, right? That's something very important as well. And finally, and this is the thing that the bosses and the management like the most, is will allow us to really, before embarking in any project, will allow us to run economics. So having a model guided by statistics and so forth will give us, for example, a P10, P50, P90, or in general a distribution of hydrocarbons in place. So therefore we can use this kind of output to create economic models, and with those models we can say, okay, we are going to do this project, or we will be keeping this project for later because the oil price is too low, or whatsoever, right? So that's another beauty, with the uncertainty, of course, involved. What type of data we have in reservoir modeling? And in general, we have two types of data. One we call it static data, and the other one is dynamic data. And as the name says, is we call it time invariant, right? So for example, you have a core, you have a piece of rock, you are expecting that this piece of rock will be more or less the same even during millions of years. It's not going to change much, right? There are situations, for example, like people say, well, porosity, we consider porosity to be static data, but porosity, once you start producing, you will see that eventually the porosity can start collapsing due to the reduction in pressure, and then porosity is changing in time, like what's happening in Ecofish and other fields in the North Sea and around the world. But in general, we consider that data to be kind of static data. And that can be divided, of course, into two. We call it hard data, and that hard data is called hard data, something that you can touch, right? Something that you're very certain. What could be harder than core or logs? Yeah, probably the hardest could be core, and the logs still there are some interpretations right there, right? There are certain parameters that can affect the outcome of the logs, right? Environmental correction, etc., etc. But still, we in reservoir modeling, we consider that to be hard data. So that data have to be reproduced in your model always. You cannot ignore that data because that's the most important data. Okay, and there is also we also have, there are some other data like soft data, and that soft data could be, as someone was asking me, how to integrate, let's say, the acoustic impedance. So then we consider the seismic itself to be soft data and in reservoir modeling, and we tend to use it as trends and soft constraints, right? It's not necessary to reproduce it perfectly, but they have some range of variability in there. And the other kind of data in general is the dynamic data, and that the dynamic data, of course, is everything associated to the fluid, right? So how, for example, the pressure and the saturation is changing with time. And then what kind of tools we can use to try to record that kind of change, variation of pressure and saturation. And there you can start talking about 4D seismic, right? You can choose the seismic today, and then you drill your wells and you make production, you make injection, etc. And let's say 15 years down the road or 10 years down the road, you shoot a similar seismic, and then you compare that 3D seismic versus the new 3D seismic. And the difference between that can give you a picture of how the fluid has moved. And that's what we consider dynamic data. Also, well tests, pressure data, etc., is considered to be dynamic data. Okay. In this cartoon, you can see how one of the fields, the oil saturation was looking at, and then certain years down the road, you can see how we have drained where the hydrocarbon was, and now the water have moved into those places. Okay. In your statistics,
Jairo,
yeah,
sorry to interrupt. I think there is one question. Maybe you can address it with the dynamic data for the seismic. So Isaac is asking, will the 4D seismic data will complement or help further in constructing 3D reservoir model?
Yeah,
is
yeah.
the question. The second question is how how it will go side by side with 3D reservoir modeling.
Talking about the 4D, right? Also the second
Yeah, the
question.
first one is about the 4D, if it is going to help somehow to construct 3D reservoir model. And the second question is, let's say, how this will help the 3D reservoir modeling and so on.
Yeah, that's right. So I can maybe try to combine the answer. We had a project. Yeah, it's okay. I can tell you the name. Let's say in Angsi, for example. Now, Angsi is one of the fields in Peninsular Malaysia, and basically we have there a 4D seismic. So the way we have used this 4D seismic to help us is we were intending to do EUR projects. You know what is a EUR project, right? Enhanced Oil Recovery Project, which is after the long period of production. So even doing water injection, etc. So we try to scratch or extract as much as we can, right? Increase the recovery factor. So we can start injecting these certain polymers to try to get a bit more of the oil that we have down there. So we have a 4D seismic there. And at that time, the 4D seismic has helped us in many ways. One of the ways was, I don't have the example here, but I will try to explain to you guys. So one of the ways was, for example, we were injecting in one of the wells, water injection, and then we know, of course, we are injecting certain amount of water in that well, right? And then we have a producer separated apart, some kilometers apart. And then we were expecting this injector to be affecting certain producers. But we saw an anomaly whereby we say, okay, this producer is not having any water cut, right? But still you could see, after comparing the 3D initial survey versus the 4D initial survey, you could see a very narrow channel connecting certain wells. So what we had done is, for this EUR, we knew we didn't know properly the connection between the wells, but with this 4D seismic, before we embarking into the EUR, which is kind of expensive project, we managed to map individual channels where you can see the variability between the initial survey and the some years later survey, the 4D. So you compare them both, and we could map the channels that we couldn't see before to model and improve the model in that sense. Another way that it helped us, it was to define the channel width, because at the very beginning we were using a channel width which was very wide, and then when you do it, sorry, I think better we, yeah, okay. I would advise everyone to.
Sorry, I will mute everyone.
Yeah.
So
Please.
because there is some disturbance, so I will mute everyone. Yeah, sorry for that.
No problem. Yeah, it's okay. So then this 4D is helping us, definitely. Indeed, we can do. The other way help us was it was very interesting, because we could even do calculations. Remember, at that time the people was very skeptic on that, but we can see we could see the amount of water that you have injected, and you can see the body that was flooded inside the reservoir. And then we try to validate and see if really it makes sense to have been injecting after certain years of water injection. That volume of water, can we see it really in the reservoir? Where's the water? So the people were saying, okay, this is going to the aquifer and whatsoever. And we say, no, this is impossible, because that's a channel. There was a channel, a very nice meandering channel going through. And in the border of the channels, after the border, of course, you go to shale, like the levee and the floodplain side, right? So the water should be there, cannot be going to the aquifer. So then we could even use the 4D seismic, difference between the initial survey and the later survey, to calculate how much water is supposed to be in that particular container, and it was matching quite well. Yeah, so there are many ways we can use it. I hope that answered the question. Any other question?
Yeah, I have a question. If you could just shed some light on variogram and geostatistics context.
Yeah, we will see. We will see
okay.
diagrams in a moment. Yeah, that's
all
cool.
right.
Okay.
Thank you.
All right, so let's proceed then. What type of variables we have in your statistics is we have continuous variables and discrete variables, right? And what is a continuous variable? Continuous variable is a variable that can take any number, a real number, okay? Not negative, but reals, okay? Like, for example, let's say porosity. Porosity could be 12%, 11%, 15, 18, etc., etc. That's kind of a continuous variable. Permeability as well, saturation as well. Now, discrete variable is a variable that only can take values integers, 0, 1, 2. And for example, 1.5 cannot be, only 0, 1, and 2. And the reason why we have to split this into two types of variables is because depends on what that type of variable you are going to model, you need to select the algorithm accordingly, because the mathematics behind each of the algorithms is different. Okay, so that's why it's so important for you to know. An example of discrete variables, as I mentioned, the most typical is the fishes. Okay. All right. Let's talk about your statistical approaches. Also, in your statistics, you have two approaches. In one approach, we call deterministic, and the other one we call it stochastic. What is a deterministic approach? A deterministic approach is basically, let's imagine that you have a certain amount of data, let's say 10 wells. When you run, you create one realization with those 10 wells. You have, let's say, your base case. And now, once you run again, with the 10 wells, you will have exactly the same realization, the same model. And that's what we call deterministic, okay? It will produce the same outcome, the same output with certain given data, always. Now, stochastic is different. In the stochastic, you have exactly the same amount of data, for example, but every time you run it, you will have a different realization. It's gonna give you a different output with the same amount of data. That's the difference, okay? And then this is just a cartoon to show you, for example, you use a method like, let's say, kriging to create a map. This is, let's say, a porosity map. You can see that with kriging having these points, so you, let's say 1, 2, 3, etc. You have certain number of wells. You can create a map of porosity, and that map could give you this picture, the cartoon that you see here, the map that you see there, right? But then you use a different method, let's say an SIS or so simulation method. Later we will talk about those methods. You could, with the same number of wells, you can produce multiple realizations, okay? And that's what we call stochastic. And we normally prefer in reservoir model a stochastic approach because they will allow us to quantify the uncertainty in your reservoir model, okay? Okay, so let's start a bit deeper and let's talk about deterministic methods. The first method could be nearest neighbor. So let's say in the nearest neighbor approach, let's say you have a grid or a map view, okay, and they say in this cell you have 0.3 or 30% porosity, 20% porosity, and 10% porosity. And now the target is how much porosity you have in this question mark right there, in that location of the field. So then you use the nearest neighbor, you will say, okay, the nearest value is going to be 0.1. So we put 0.1. And it's deterministic because no matter what happens, always for the yellow question mark that you have there will produce 0.1 if you are using nearest neighbor, right? Now, with arithmetic mean, of course, another approach you could say, okay, rather than having the closest value, what I would do is I would add them all, get a summation of all, and divide it by the number of samples, and then you will have an average, let's say an arithmetic average, right? And there could be also logarithmic average, etc., etc. But that's kind of another approach. And no matter what you do, if you're using the 3 points, the same 3 points, you will get always the same arithmetic mean. So meaning to say it's a deterministic method. Now, other deterministic methods a bit more advanced could be, for example, interpolations. Linear interpolations could be in 1 dimension. It could be even in 3 dimensions, right? And for that linear interpolation, the idea is that, let's say you have a known value here and a known value right there, and you would like to know at the P0 what is the porosity, for example. And then the idea is that you could take distances, for example, the distance 1 between P0 and P1, the distance 2 between P2 and P0, and then you can calculate more or less kind of a weightage according to how close or how far you are for certain value, and you can determine the porosity right there. And the same way you can do when you are doing in a 2D. Now in a 2D, you could have, let's say, 3 points here, and you are trying to estimate right here in the center. And again, you will have all the distances in between the points, and you can come up with the weightages according to those distances to calculate what is going to be your porosity right there. And these are deterministic methods, right? The other deterministic, which is the one that we use the most in the oil and gas industry is the kriging. And the main difference with kriging and the other interpolation methods is now that the kriging is considering what we call the variogram model. But at the end of the day, the idea is that the prediction, let's say in the yellow cell that we have there with the question mark in red, the prediction is going to be a combination between whatever you know. Okay, in this case, you know 0.3 there, 0.2 there, and 0.1 here, with a weightage. It's always a weightage. So it's very common in these deterministic methods to have a weightage right there. And this weightage is calculated using the variogram model, which I'm going to explain a bit. The mathematics, I don't want to go into the details of the mathematics. It's a bit tedious and so. But the idea is that there is a weightage to be estimated, and that estimation in kriging, it will come using the variogram model, and of course you need to solve a matrix to try to get those weightages right there for you to predict the value at that location. So then let's talk about variogram. Oh, before we talk about variogram, let's see the main difference between kriging and simulation. Remember, this is deterministic and this is stochastic, right? So if we look at into the details in this cartoon, you can see a person going from one point to another, and he's recording let's say the length of cable in between. So the idea is that he take a measurement right here at the red points that you see there, point, he take this measurement, and then in between he doesn't know. So if he's using kriging to estimate in between, he's going to give him the kind of blue line that you see there. It's kind of a smooth interpolation. That's kriging. Okay. But if he's using a simulation, he can run as many simulations as he wants. So you can see that in simulation 1, it's going to give him the black color line. In simulation 2, you can get the red color line, right? So it's honoring the points. You see the points is here, the point is here, it's honored. But in between, there are fluctuations. So as you can immediately can see with the kriging, which is the blue line, it's smoother, right? So then with kriging, you cannot produce the maximums and the minimums, right? The highs and the lows. But with simulation, it's kind of nice because you could estimate highs and lows that sometimes in the data, especially in the geology, you can have these kind of highs and lows, right? So you are, let's say, modeling an area where you are having perm streaks, high permeability beds, for example. You wish to have those highs also. You don't want to smooth them out because that could have implications. Okay. Then in the right side again is a simulation. This is already coming from a 3D where you can see the input data is basically the same. This is supposed to be the true, so you can compare. This is the true. And now what's going to happen if you use kriging? Of course, if you use kriging, we will have one single realization, which is this picture right here. So then you can compare the true versus the kriging, and it looks, you can see a bit smooth, right? It's a lot of smooth. Remember, this is the input data, the points that you see right there. And now with simulation, you can create the pictures below. You can create as many as you can. So you will see more variability. You will see more streams happening. You won't see a very smooth realization. And the beauty of this is since you have many, so then you can quantify the uncertainty. What's happening in there? You can quantify as many volumes as you wish, and then you can rank them. You can select percentiles and tell what could be the range of the volume. But in kriging, you will have only one single volume, right? Now, some people say, well, kriging is not deterministic. If I change the variogram, because the variogram is a parameter inside kriging, I will have a different realization. That's right. But now you're changing the variogram, right? So the idea is that with the same input, without touching the input, you will always have only one outcome with kriging. Let's talk about variogram. So the variogram is the measure of the lateral continuity of any property. It could be a discrete property like phases, or it could be a continuous property like, let's say, porosity, neck-to growth, etc. So it will tell us how similar or how dissimilar is my property from one point to another point. So and for doing the theory of that, I will play a video so you guys can see the video, and I hope you can listen what they are saying. And then I will tell you what is the implication of the variograms, okay? So pay attention to the video. Let me just play the video. I don't know. We just, okay. You tell me if you can hear what this video is saying. Variograms. Can you listen?
Yes, yes.
Okay, cool. So I play, okay? I'm here listening to the video with you guys. A variogram is a plot of variability as a function of separation distance. We use it to model the spatial and directional continuity among data points. The variogram helps us to quantify the relationship between variables over distance. Using variograms, we can show that reservoir properties between wells which are separated by a small distance tend to be more similar than those properties seen in wells that are farther apart. We can use that information to predict values of reservoir properties at unsampled locations. In this video segment, we will show how vectors and bins are used to specify data points to calculate the experimental variogram. We will also describe features and interpretive aspects of the variogram. In geostatistics, we search for data within bins, rather than searching along a simple vector. Bins are designed to take the vector components of azimuth and distance, and divide the distance component into equal units of lag distance. Bins are defined by lag distance, or the separation distance h between sample points used in the variogram calculation. Lag tolerance, which accommodates data that do not reside on a regular grid pattern. Lag tolerance is commonly specified as plus or minus the initial lag distance. Search azimuth, used to design search strategies along specific directions, when reservoir properties are more continuous in one direction than in another direction. Search azimuth tolerance, the angular tolerance in degrees that limits the directional search around the specified azimuth. And bandwidth, which restricts the limits of azimuth tolerance at all lag distances. Review the subject text for more information on these methods. Search strategy is dictated by the data configuration and the number of sample points. When reservoir data is sparse, you'll need to conduct an omnidirectional search. Set up the omnidirectional search by selecting a single azimuth direction. It does not matter what angle is selected, and then setting a 90-degree azimuth tolerance. Here's a search neighborhood design based on an omnidirectional model. Properties that differ in magnitude with direction are said to be anisotropic. For example, when horizontal permeability within a reservoir differs from vertical permeability, then permeability is said to be anisotropic. Variograms should conform to the major axis of anisotropy. Therefore, we need to align the search axis in that direction. This is an example of a search neighborhood design based on an anisotropic model. The variogram correlation term, gamma, is a measure of dissimilarity expressed by increasing variance as a function of distance. The variogram is the sum of the squared differences of all data pairs falling within a given lag bin, divided by twice the number of pairs found for that lag. Now let's point out the features of a typical variogram. The origin is the intersection of zero lag distance and zero variance. Lag is a unit of linear separation distance between points. The user specifies the unit distance, for example, 200 feet. The variogram function is the model of variance, or dissimilarity, as a function of increasing lag distance. The nugget is the vertical distance between the origin and the point where the variogram intercepts the y-axis. Ideally, at zero distance, 2 points should have zero variance. However, when random noise, short-scale variability, or measurement error causes a discontinuity at or near the origin, this uncertainty factor is attributed to the nugget effect.
The CIL is the variance for the dataset. The CIL represents the maximum amount of dissimilarity, or variance, between points in the data. The CIL is a plateau of constant variance. The range is the distance at which the variogram reaches the CIL. Beyond this distance, variance is constant, and all points will be independent of each other. This represents the largest separation distance of related data points. So, what does the variogram show? Reservoir properties tend to correlate very closely at small distances. The properties become progressively less and less similar to each other with increasing distance. As differences become larger, variance values increase. Beyond the maximum correlation range, the squared between points no longer increase, and the variogram develops a plateau called the CIL. Any points beyond this range are so far apart that they no longer relate to each other. These variograms show examples of geometric and zonal anisotropy. Notice the relation between CIL and range. Geometric anisotropy shows a change in range while maintaining the same CIL. With zonal anisotropy, you'll see a change in CILs while the range remains the same. Now, let's show how the variogram affects your prospect model. This example shows a sequence of variograms, each accompanied by a Krieged image and conditional simulation. The CIL and ranges are held constant throughout the sequence, while the nugget progressively decreases from left to right. The CIL is set at 1.0 gamma. The variograms show geometric anisotropy, with a major axis of anisotropy set at a range of 20, while the minor axis is set at 5. This anisotropy is reflected in the accompanying images by a linear trend oriented at north 45 degrees west. By definition, the direction of minimum continuity is 90 degrees to this azimuth, or north 45 degrees east. Adding constant variance over all scales increases the value of the nugget. As the nugget increases, the Kriging values smooth out, tending more toward the average. The nugget adds variability during conditional simulation. In the Krieged images, notice the data locations start to appear as the nugget increases, and are very noticeable at 100% nugget. This shows how Kriging is an exact interpolator when data values lie exactly upon a grid node. Kriging shows a smoothing effect as you proceed from 0 to 100% nugget. With 0% nugget, Kriging produces the global mean value at all locations, except at the data points. By contrast, the conditional simulations show a purely random pattern. This is expected, because simulation is meant to preserve variability, not smooth it. Increasing the nugget increases the variability.
Okay, guys, just give me a second.
I have a quick question here. You're muted, I guess.
The question,
Yeah, I think you are me.
what is the question? Sorry, I was having issue here. Go ahead, please.
Sorry, Dr. Haile, I don't have the chat option. Otherwise, I would have asked question on chat. So
No
the
problem.
question is, in fact, how do we compare and contrast the variography and the anisotropy? It's very fine difference, I guess. So, thank you.
Yeah. Let me just explain to you a bit of the video in this one, okay? So basically, as the video said, the variogram is trying to compare pairs. First of all, you are trying to compare what happened in this location versus what happened in this location. How similar or how dissimilar is the property that you are investigating in these two pairs, right? In these 2 points. So then the relationship between, let's say, porosity and porosity will tend to be more related when the points are close, and this relationship will tend to disappear whenever you go far away, right? So the first thing you need to do is you need to do an experiment and create an experimental variogram to create the points that you can see in my, let me just put the highlighter again. So all these points are the result of that comparison between pairs, right? So this is what we call the experimental variogram. And then since the software cannot use the experimental variogram, which is the discrete kind of representation of those pairs, you need to create a model. And the model is kind of a fitting line to those points, right? Now, as you saw in the video just now, there are certain parts of the variogram which are very important. So first of all, in the x-axis, you will have what we call the lag, which is a distance, separation. What is the separation between the points, right? And in the vertical, you will see the variance. And the variance is basically the difference between this porosity. If you are investigating porosity, this porosity and this porosity, you can calculate the variance at that particular lag distance that you have to decide. So you need to decide what is the lag distance in between the points, right? And then what is happening is when the distance start increasing, there will be a point where you don't see correlation between the points, right? And this is what we call the range. At that distance is what we call the range, that horizontal distance. And then the variogram will tend to develop a plateau. When you have a lot of information, this can happen, which is not normally the case. Normally, you don't have a lot of data to do these things. But the only thing for sure is the variance start increasing until there is a point that there is no relationship, and it would tend to start decreasing. So that's where we pick what we call the range. And now the nugget effect, as the video was showing, is telling you kind of the noise in the data. Normally, we don't use the nugget. We normally consider the nugget to be 0. And the reason why we consider it to be 0 is at this location, if the distance is 0, which is a lag distance of 0, you are expecting that you can reproduce exactly the same value. So you take a measurement of porosity here, and you go again and take the same measurement, you're expecting the porosity to be the same, not changing much, right? But due to the tool, for example, sensitivity of the tool and so, you take 20% and then you take a measurement again and take 22% and then 19%. It's low variations right there. That's what we call the noise in that particular part. And that's what the nugget is trying to do, capture that variability. We normally in reservoir models we use nugget equals 0. Normally we don't use it. Now going back to the question that you asked me, how we know the anisotropy and what is the implication of the anisotropy in the variogram. So there are two concepts to be understood. First, isotropy and the other anisotropy, right? So if isotropy means the property is behaving similarly in all directions. So meaning to say, if you have a range of 1 kilometer for porosity, that will be the range everywhere, right? But that's not normally the case. Some carbonates tends to have this kind of isotropy. But then the most common case is anisotropic, which is having a longer range in one direction and having a shorter range in another direction, right? And this is basically what we have in this cartoon. So you could have a very long range, let's say the range 2, and a short range in this direction. And what is the implication? Sorry, this is drawing crazy yellow lines. But what is the effect of that is, for example, if I give you this picture, and if I ask you, what is the azimuth that can produce in the azimuth in the variogram that can produce this picture, definitely you would say the azimuth is in this direction, right? It could be, let's say, 45 degrees east, right? This is the azimuth. And now, if I ask you, what is the range, the major range of this picture, you would say the major range could be from here to here, more or less this distance, which is kind of the reddish color that you see, the continuity that you see, and then starting the grading, right? And what is the minor range? The minor range is in this direction. Because you can see that, let's say if this is porosity, you can see that the porosity tends to degrade rapidly in that direction rather than in the major direction, which is the north 45 degrees east that I told you before. So then that's kind of the way the bariogram can help you to control your realizations. So first of all, you need to investigate and say in which direction your property tends to be more connected. So you will have 360 degrees to investigate. You can do baryograms like in this picture, they are doing a baryogram in the north-south direction, then another one in the north 45 east direction, then another one in east direction, and so forth. And then what you are doing is basically you calculate the baryogram in the north-south direction, then you turn around and calculate in this direction, in another direction, until you cover the 360 degrees. So you have different experimental baryograms in each direction. Then you create a model of each of them, and you take the range in each of them. This is range 1, range 2, range 3, etc. And then you can see which one is the measure of those ranges. Let's say it's range 1, for example, or let's say range 2. Okay, and then you say, in that range 2 is where I'm expecting to see more connectivity of my property. So the property will be more connected in that direction. And in the direction perpendicular, which is the minor range, it will be more changes, right? It's more variability in that particular direction. Okay, is that clear?
Yeah. Just wanted to, can we say like if we introduced variogram and we have taken care of anisotropy? Can we say that? Or
anisotropy depends. First of all, you need to know you have or not, right? As I said, you have two options, or you have it or you don't have it. Normally you have it. So for you to know if you have it, you need to do baryograms in different directions, right? And then if you, after you have done the experiment, only then you can say, oh, my model, I will introduce anisotropy, right? Because that's what the data is telling me. So you cannot introduce it by force, but you need to let the data tell you if you have anisotropy, okay? You understand what I'm trying to say? Now, of course, if you want to put heterogeneity, perhaps this is what you would like to ask about heterogeneity. If you want to put heterogeneity in your model, and you would like to put a more heterogeneous or a more homogeneous model, if you wish. So then you put shorter baryogram, for example, smaller ranges, you will have a more patchy, a more discontinuous realization. Then you will have a more heterogeneous realization of your model. But then if you put a baryogram range which is big, 1, 2, 3 kilometers in that direction, and let's say the same direction, so it's going to be more homogeneous, your realization. Okay, something like that.
yeah, got it. Thank you.
All right, Jairo, there is one question regarding the negative effect. So
yeah.
Ainul is asking, so is it better result when the negative is equal to 0?
I mean, the question you need to ask, first of all, let's try to understand again what is nugget. What is the nugget effect? Okay, so the nugget effect is the difference at the distance 0. You see, the distance is 0. The horizontal axis is distance. At the distance 0, let's say this is the distance 0, right? So what is the difference of the property at that distance? See, you have 20% there. And then you compare again this at the same location. What is the difference? The difference should be 0, right? Because it's at the same location. It's at the distance of 0, right? So then for you to justify that particular property, which you took a measurement, it was 20%, for example. Now it's not 20, but 21%. You need to explain why. And you would say, oh, okay, because the tool that I put, I calibrated the tool differently, and now it's giving me a noise kind of thing, right? Okay, that's the concept of nugget. So you consider that that's happening, so then you can do it, you can use it. But if you do that, what you are doing is you are putting more heterogeneity in your realization. Remember in the video, they show you how if the nugget effect is 0, and then when you start increasing the nugget, I mean, when you start increasing, instead of the baryogram to be at the 0, 0 location, is having a variance at the beginning. So it will give you a more kind of pixelated, salt and pepper you wish realization. So then the question of nugget is, I normally don't use it, okay, because I don't consider this kind of variability to happen so critical, let's say, so big, if you wish. right? Because at the same location, you are confident what you have at that same location. But then if you do it, what you are doing again in your realization, you will put more kind of heterogeneity, more pixelated kind of thing. It's not going to be a smooth realization, but a lot of pixelated. Okay. So then again, you need to let the data tell you. You need to do the analysis. You cannot make a decision a priori. You cannot say, oh, I will put an isotropy at the north-south direction. No, you cannot say that. You need to first, with your data, if you have enough data, this is another issue for bariographs, right? If you have enough data, so then you need the data to tell you what is the direction, what is the nugget, what is the range, etc., etc. Now, the main issue with variograms, which is something that you need for any geostatistic algorithm, you need variogram, except for object modeling or MPS. Later, we will talk about those methods. So you will always need a variogram, right? And the issue is for you to create a very high confidence variogram, you will need a lot of data, which we normally don't have. Now, what we do when you have only one well or two wells? How do you variogram for the 3D? You cannot, right? So then there are other things. You can take, for example, the seismic. You have the seismic cube, and in your seismic amplitude is telling you example, that is telling you something about the geology. You can leverage on the seismic amplitude variogram to try to create your variograms. In the best case scenario, what we do is basically we find an analog, we go and find a field close by, which is having a similar depositional environment, and we say, okay, in that environment, which is the same short phase that in here, in this particular unit, I can borrow from that field the variable analysis, because in that field they have a lot of wells, for example. Then we just borrow the azimuth, the range, major range, the minor range, and the vertical range to create the model, okay? So yeah, so that's kind of the story of the nugget, and we normally don't use it much. We prefer to use a nugget at 0, but again, you let the data to tell you, okay? All right. Now, in this example, this is a real case example. We need to start moving a bit faster, I think, because we are less than the middle, I guess. This is an example in another field where you can see in the map view seismic attribute extraction, where you can see the direction of those bars that you see right there in the color. And then in the top corner picture, you can see the experimental variogram that I have done. So you can see here at 0 degrees and 45 degrees, etc., and 135 degrees. And then the idea is that you will create all these ranges at different orientations, and at the end you can decide and say, oh, okay, my anisotropy direction is basically in that let's say northwest direction, okay, and my major range is going to be whatever measurement that you have taken here. For example, this particular, I don't know, 2 kilometers is the range in that particular direction. And in the perpendicular direction, let's say this one, you can say that your range is smaller and is, let's say, any of the values, let's say 2-3 kilometers smaller than the big one, okay? So this is a real case example. The idea is that you will need to do variogram per each zone. So you have different reservoir, different zones. The idea that you do variogram per each of them, you cannot lump them together. And also you will need to do variogram per each particular phase. So you have 3 or 4 phases, you need to do variogram independently for each of them, okay? And then you use it in the software. Okay, let's have a probably 3 minutes, no more than 3 minutes break, and then we can go to the next part of the presentation, which is phases modeling, property modeling, and sensitivity and uncertainty, okay? Think about questions, and after the break, we have a session of questions and answers, okay? And we do a break now for 3 minutes. So we'll be back at 3:27. Okay, guys?
All right. Thank you, Jairo.
3 minutes. Yeah.
Yeah. Okay.
I think let me on my
Okay, 3 minutes has passed already. Now we are a bit kind of at the middle of the presentation. So any questions so far? I know variograms, I used to include in the lecture the methods of how to calculate the variogram, but unfortunately due to time constraint, we don't have the time. So I will encourage you guys to try to go to the program master. You have a master program, and in that master program we go into more details on what I've been telling you about your statistics, right? So then at the end also I will give you my email, so if you guys have any other question about variograms or how to do it, you're welcome to send me an email, and I'm willing to teach you a bit further about the topic. Okay, any questions so far?
Yeah, just if you could just quickly comment on Bayesian algorithm for geostatistics, and also what Petrol is using.
All right. Okay. All right. Okay. I think I know we have a mixed participants, well advanced, and then we have also our undergraduates. So, with respect, I would give priority to the undergrads. So I think we better cover the content. Then later on a personal base, maybe we can.
Yeah, exactly.
Jairo,
I would advise the same. Yeah, I would advise the same, because each of these topics could be as deep as you wish, right? Like we can dedicate 1 week for purely statistics or just statistics.
That's right.
Otherwise, we can miss the objective. Remember, the objective is to give you a flavor, kind of high level flavor of how we use the reservoir characterization inside the model, and how we, big with the statistic, how we touch, how we can try to integrate these things. But again, the details, we cannot go into the detail, the equations, the mathematics, and so forth, because I think the presentation is not intended for that. So just shoot me an email, and I will do my best to.
That would be ideal, I think. Yeah.
All right. Okay, so now once you have created, remember the container, you have already your 3D container already. I more or less show you how we did, right? And then you have done, you already understand a bit of what is behind the scene, and what is your statistics trying to do, right? Your statistics trying to use the multiple information to predict away from the observation data points, to predict away that particular property. And then you can do for any property. Remember, you have discrete and continuous properties. So any property can be predicted using your statistics and so forth. So now let's start with the next step. So once you have your container, now let's start imagine how the fishes, how the geology will be represented in that particular container. Okay, and this is what the step we call the fishes modeling. So in the now, let's start talking a bit about a well location, what happened at well location, and then how we propagate that away from the well location to produce what we call the lithophases up to here. Then later we do property modeling and uncertainty analysis. So let's focus on this particular part at the well location, the prediction away from the well, and then the 3D itself. This is what we're going to do in phases. So what is a facies really? A facies is, we call it, is a piece of rock, if you wish, with certain characteristics. And those characteristics could be as different as, let's say, color could be a characteristic. Let's say granulometry could be another characteristic. The texture could be another one. So anything different is what we call facies. So we have to be careful when we are doing a core description, because you can end up with tens or 20s or 30 number of fishes. And of course, we in the reservoir model, we don't want to model so many fishes, because at the end, if you divide the data into many clusters or many fishes, you can end up having a lot of fishes without much information about them, right? So at the end, you need to compromise, and you need to lump some of them together. So you have a core description report, you will see that they have 20, 25, even 30 fishes. But then in a reservoir modeling, normally you have between, let's say, 3 to 4, maximum 5 fishes, okay? So I mean to say, you need to lump them together with certain understanding, to lump them together, so then you can model accordingly. So in here you can have you have an example of what we call a depot facies. Remember, depot facies is kind of a bigger picture, and then inside that depot facies you could have multiple what we call lithofacies, right? So in this example, you could imagine a finding network sequence can represent a channel. And in that channel, the channel itself, let's say the big channel itself, internally, you can split that into, let's say, the conglomerate or the lag deposit at the bottom, and then you can have a more coarse sand at the middle, and then you have a fine sand at the top, and these three can be split into phases. So the idea is that you would take the description. This is the core description, okay, which is a qualitative description. And this is a real example. You go to the core, you go to the warehouse, you describe your core, and you make a description. What is the description? They say, okay, I have a sandstone, a yellow color, yeah, I have a limestone or whatever. They describe it in words, qualitatively, right? But even this is very important to have for the interpretation. You cannot use that into model. You need to translate that into numbers. And how we do? So basically, we take the ranges, for example, from here to here, an example, interval range, and you say between here and here is the same lithology. So you say between this range to this range, for example, the same lithology. So then you assign a discrete value to that particular lithology. Let's say 1. So from here to here, the same. And then you go to a next interval, and then you say my lithology changes, to here, and then at the end you have another one. And then you can say all of them, they belong to the same EOD, or the same depot phase, let's say channel, an example. So now you try to translate all the qualitative information into numbers, right? And for doing that, of course, you can start also working with cross plots. You can do a cross plot porosity permeability, and then you try to cluster. You say, okay, even though I have 25 or 30 phases, this phase has been deposited in channels, and they are more or less clustered in the same kind of poroperm area. Then I can lump them together. So that's kind of a method that we use to lump these phases together. Okay, and you will produce a well log, and in that well log you will have a discrete value, a well log which is 0, 0, 0, 1, 1, 1, 2, 2, 2, according to the lithology that you have in the core description, right? Now, if you don't have a core, for example, you could, as I said, you can analog. You can take an analog and say, okay, in this analog, they are using for example, B shale and porosity cutoff to define what is reservoir and non-reservoir. So you can borrow that kind of analog information into your field, and you can produce your phases, right? There are other advanced methods, like, for example, artificial intelligence, which is very, very kind of in fashion nowadays, right? And we can use neural nets, for example. I've used neural nets to try to predict away from the core interval what is going to be your phases in using the well logs, for example. Okay, so why do we need phases at the first place? Definitely, you will need to capture the reservoir architecture, right? This is the purely stratigraphy and sedimentology information. You need to do that. If you don't do that, meaning to say you are ignoring the sedimentological description or interpretation. And that's something that you should not do, right? Because remember, at the end, you would like to utilize and you would like to maximize the use of the data that you have, right? Definitely, you will capture your concepts. Later on, you will see how we create a concept. I will give you some examples. Then it will help you also to run sensitivity and uncertainty analysis, because even though you don't know how much, for example, one particular phase you have in the 3D volume, you can sensitize that value. So let's say you have in the wells 30% of sandstone, right? But then it's at the well location. You don't know between the well how much could it be. So then you can sensitize how much of these phases you would like to put in your model, right? And it will help you to create equally probable realizations. And this is where we use the geostatistics to do that. And when we say equally probable is, since the data is the same, right? You're using the same data to create these realizations. They have the same probability of happening, all right? You can run detailed volumetrics, meaning to say, if you have 3 phases, let's say sand, silt, and clay, and then you already modeled 3 phases, you could quantify how much volume you have in these phases sand, in these phases silt, and in you wish, let's say you would like to calculate something in the shale, you can also do. And then you can make decisions. You can say, okay, we have always in the field, we have perforated, let's say, only the sand. But we have never tested, for example, this kind of siltstone, right? And we know in the siltstone you could have let's say, I don't know, 10% of the volume. So then you can quantify and say, oh, it's worth it to make a workover, and we can perforate one of these siltstones so we can see we can produce for those siltstones because we have 10 millions. So eventually we can have certain behind casing opportunities, for example, certain rocks that we haven't perforated before. And we know how much volume, since we have the facies, we know how much volume could be associated to those particular rocks, and we can see if a project can be worth it or not. And definitely, if you capture the facies, definitely assuming that you don't have a very high diagenesis happening, you could try to understand the communication in between the wells. There are certain instances where you drill a producer and you drill an injector, and then you start injecting and you don't see the effect of the injection in the producer, but there is nothing in between. Let's say you don't have any fault, a clear fault seen in the seismic. But then when you do a detailed facies model, you could represent those kind of bafflings or those kind of, let's call it barriers if you wish, that cannot be seen using faults or other kind of things. If you don't have the facies, of course, you cannot do anything, right? So you cannot capture these kind of concepts. Okay, so now, again, this is I remember I told you that we sometimes have too many facies and you would like sometimes to lump them together. One of the ways is using a crossplot. And another reason why we need the facies is because we tend to see, especially in the clastic reservoirs, that there is a clear relationship between the porosity and the permeability with the facies, where your best facies tend to be placed on the high levels and your worst case, your worst facies tend to be in the low side of porosity and permeability. So then if this relationship is still there, so meaning to say, if you capture your facies, you would control better the distribution of your petrophysical properties, because somehow there is a relationship between them. And that's kind of the case that we are wishing to happen always, especially in clastic. But then what happened in carbonates? In carbonates, when you try to do that poro-perm crossplot, you will see that there is a mess, right? It's a big cloud, the uncertainty is very high. You cannot say the red is always in the high, but because you see the red happening in the lows and so forth. And the reason why this is happening is because, as you know, the level of diagenesis happening in the carbonates is highly, the carbonates are highly affected by diagenesis rather than some of these clastics, right? So sometimes, I tell you, in some projects in Iraq, for example, and some of them in the Gulf of Mexico, in the inland, we did not use, or in the Middle East, I work also in the Middle East in some project of carbonates, and sometimes we don't model facies on those. And the beauty of those carbonates is that the seismic was working so nicely that we can go porosity directly from inversion studies into the model. So we don't need to capture facies. But ideally, as I said, you should try to do your best to capture your facies, because one of those reasons is because you can later leverage that facies to try to predict your petrophysical properties. Okay, this is an example of how I use a neural net approach to predict away from the wells the facies that I observe in the core. So you will see a series of wells. You see the well E2, 4, etc., and then you will see some tracks in color. So the first one is, I think, the gamma ray colored by porosity, and then you will see a track which a lot of colors, right? So the first track is basically the description that we have at the core. This is what we know, right? And now the second track is facies that were manually interpreted by the geologists. So in this well, you have a core, and in this well, this track was interpreted manually by the geologist. So the geologist is doing like kind of a neural nets is doing, right? So he's looking at the well logs and he's training his brain to say, oh, okay, whenever the porosity is high and the gamma ray is low, I have this particular facies. So he's training himself to try to predict this. And then this is a given kind of interpretation, right? And now you can see the track number 3, which is common in all of the wells, is how we use the neural nets to predict the facies that we have seen, okay? And then what we do in neural nets is you have, not all of the wells will have core, right? Some of them. So you keep 1 or 2 wells with core in your pocket and you train your neural net. So you try to create a mathematical model to predict using the well logs to predict the discrete log, which is the fishes. And then once you have this mathematical model, you try to see how that mathematical model applies into what we call the wells that you keep in your pocket. You bring your wells in your pocket, and then you plug the mathematical model and you predict. And then in that particular well, that's what we call the blind test. In that particular well, you also have, of course, a core, and then you see how the mathematical model is predicting that particular core. And then if this prediction is too off, what you need to do is you need to go and fine tune again your model, include or exclude another well log, for example, and then you create another mathematical model to predict the fishes, run it again, and then you do a kind of an iterative process until you more or less feel satisfied and say, okay, the error is very small, and I can see that the prediction is more or less accurate. So once you finish that training process, predicting with your blind test as well, so you have a model, and that model is an equation. Imagine yourself having an equation. This equation is in your project. You can have it in your project. You can borrow to another project. You can take it with you whenever you move around. Whenever you go, you can apply in the same model, as long as it's a similar, let's say, environment of the position and so forth. Now, what is the disadvantage of these methods is you have to be careful because they are based on well logs, right? So in the well logs, let's say you have a field with wells logs taken in the 70s, and then you have drilled wells recently in the 20s. So of course the tools are a bit different, right? Even though gamma ray is gamma ray, the people will see big differences when they run tools in the 70s than they went running to with the new generation tools nowadays. So then you have to be careful with this kind of standardization. You have to be careful with the corrections, environmental correction of the well logs, etc. Because you are doing certain corrections in certain wells, and in other wells you haven't done that. When you try to integrate the same mathematical model, you can have outcomes that are not really consistent. So those kind of things you have to be careful. It's very beautiful, this method, because with this method, you can predict in a blink of an eye, very fast, thousands of wells if you wish, the fishes at the well location. You just plug and play, and in a few seconds, and the software predict the fishes in all the wells, okay? Of course, requirement will be that you will need to have in those wells the same set of well logs that you use for training your neural net, right? So meaning to say, if in your model, mathematical model of your neural net, you need the V-shape, and there are some wells that they don't have V-shape, so then the software won't predict those in those wells, right? So then eventually you would ideally, I would say you could have 2 or 3 models, mathematical models, and you will say, okay, whenever I don't have, let's say, density log, whenever I don't have porosity log, I can plug and play this mathematical model that is not required in this particular well log. And whenever I have the full set of logs, I can apply this more complete equation or mathematical model. Okay, so this kind of a bit advanced method. There are other methods like, for example, cutoff, right? You can also go and start with the core description, and you have your B-shell and your porosity, and you can start applying in the calculator. You make in the calculator, say, okay, the porosity, let's say, is more than 20%, and the B-shell, let's say, is less than 40%, make fishes 1. Then you can predict with that cutoff, right? And then you adjust the cutoff until you see that you are reproducing the fishes that you see in the core. Then once you have fine-tuned those cutoff, so then you have the equation as well. It's an equation. It's less advanced, but it's still the equation, right? You will say whenever porosity is this and B-shell is this, and you wish you can put any other well log, whatever, then you can predict your fishes away from the core, okay? So then what do you have at the moment? You have a 3D grid. It's in place already. You have captured the interpretation from the geophysicists, the faults, etc. Right? Now at the well locations, wherever you have a core, now you propagated the fishes description away from the core. So all the wells, let's say you already have core, but everything is at the well location only, right? So now you are ready for the next stage, which is how to propagate, how to predict away from the wells those fishes. Of course, using your container. You have your container, you have your wells, you put your fishes at the cells that has been penetrated by that particular well. So those cells are already containing a value of fishes. And now let's see how you wish extrapolate or how you model away from the wells. Okay, and for doing that, the first step is you need to create a concept. Okay, you cannot just simply push a button in the software and let the software create a model. You need to create a concept. Okay, for that concept generation, there are a lot of methods. This is an example in Venezuela where we extracted from one of the PhD theses a very nice study in the Boyacá block. This is in the heavy oil belt in Venezuela. And then there were some issues. They couldn't do history match the production and so forth. So then what we did is we have taken these studies, very detailed studies, where basically the same methodology. We did the thesis. He mapped this with his hand and draw with pens and whatsoever, integrating the information that he got. And he strongly believed that what was happening is in the western side, he was expecting to see more mouth bars, and in the eastern side, he was expecting to see more channels. And some of these channels were braided, and some of them were a bit more meandering. This area is a huge area. So then we leverage on that knowledge. We created the trend maps to create a concept where we said, okay, wherever we are in the east, we are expecting to see more mouth bars, and wherever you are in the west, you are expecting to see more channels, braided or whatsoever. And then we created a concept. That's the way we can create a concept. There are other ways to create concepts, like, for example, you can leverage on the seismic. Sometimes the amplitude works nicely when you have a very high quality seismic, and it can help you to pinpoint your concept as well. You can extract them, you can manipulate them, you can draw polygons, you can cut and paste, you can edit, etc. Until you create a map that can be helping you as a trend map, how to control your phasage distribution. That's what we call a concept, right? There are other concepts that we can extract from analogs, and these are studies. This is another paper published somewhere where we were working in a project in Cuba, and we extracted information using a satellite like Google. You know, we are very familiar with Google Earth. You can go Google Earth and you can take measurements. You can say, okay, the mouth bars could be this big, the channels could be this width, and so. And we believe that this Miocene reservoir, it looks more like nowadays how this coastal area of the southern part of Cuba looks like. And then we capture this information, the sinuosity, etc., to create an object modeling based on that particular analog. Okay, you can do that as well to create the concept. Let's talk about the algorithms. Once you have the concept, and the concept, some people call it the geofantasy, right? It's something like it's coming out of your interpretation itself. Remember, you can create as many concepts as you wish, and your statistics will allow you to capture them. So it's not a problem. So now that you have your concept, you have your phases at one location, and you have a concept. You say, okay, I want this model to be like this because the data is telling me, because the seismic, etc., it should be like that. So now, what kind of algorithms do we have in the softwares and in the statistical methods to propagate or populate these phases? Okay, so in general, you could say that you have pixel-based methods, if you wish. Okay, we call it pixel-based methods, and this pixel-based method could be using 2-point statistics. What is 2-point statistics? Are those methods that are based on bargram. Why 2-point statistics? Because what you are doing is you are comparing how a property is changing from one point to another using data pairs, right? 2 points. So you compare from here to here, then another pair here, depending on the lag distance that you have selected in your bargram. Okay, this is 2-point statistics, but still pixel based. So assuming pixel based. There is another method that has been developed, like probably, I think 15 years ago or maximum 20 years ago, that we call multi-point statistics. This is MPS. And multi-point statistics is different than 2-point based statistics because now, as the name said, it's multiple points. So now you would create, instead of using a baryogram model is a 3D representation of the spatial variability of the property, right? So now, instead of having a baryogram model, what you will have is basically a cartoon itself. It could be, they call it training image. You could have a representation of this cartoon where in that cartoon you will capture the proportions, you will capture the transition between the phases, you will capture the continuity of the phases, and so forth. Okay, the shape of the phases, the size of the bodies, all can be captured in that kind of training image. So therefore, for multi-point statistics, you don't need baryogram. You just need to have this particular representation where you are capturing everything, including the spatial variability. Okay, so no variable required. For the 2-point statistics, both of them are pixel-based, 2 points and multi-points. So for the 2-point statistics, you will have two methods, two main methods, which is the sequential indication simulation, SIS, and the other one is truncated Gaussian simulation. We will see them in a short while in details, okay? So sequential indication simulation, truncated Gaussian simulation. And in something in between, which also it does not require barograms, is what we call object methods, object-based methods. And in those object-based methods, the idea is that you are telling the software what sort of objects, three-dimensional shape, three-dimensional objects you want to populate inside your model, okay? So you believe you have a kind of mouth bars, so you will define them as a fan with certain width, with a certain length, etc. Or if you want to put channels, for example, you will define the channel direction, the channel's width, the channel thickness, the proportion of those channels, and so forth. And what the software is going to do is, having the input data that you are providing to him, he will, in an iterative manner, he will create an object according to the specification that you have give. He will put the object inside the model, first constrained to the wells, and if this object satisfies your input data plus the wells, the object stay inside the grid. If it's not, it cannot satisfy, let's say, one of the wells, so it's rejected. So he will create another object and he will attempt to do the same. Try to put that object inside the 3D grid until he finds a match, right? So as you can imagine, it's a very time-consuming process, because if you have multiple wells, let's say hundreds of wells, so there are too many points to control the object. So the software can go back and cannot find the solution. And there are instances where the software cannot finish. It can take days and you cannot finish any single realization. So then you can immediately imagine, if you have too many data points, for you to create an object model, it could be a bit challenging for the machine and also for you, because you need to. Let's see the methods, and then I give you advantages and disadvantages. So the first method developed was SIS. And in this SIS method, as I say, is based on the barogram. Of course, the statistics is behind. It can honor the distributions. It's a very flexible for the parameters. It's very easy to run. It's very fast. So it's a blink of an eye, you can finish a model and so forth. But there are certain disadvantages. One of the disadvantages that the people noticed at the very beginning was that realization that these models produce were a bit unrealistic in terms of geology. So you cannot see the object, you cannot see the transitions, right? So then the people say, well, I'm expecting to model a channel, but using SIS, I cannot produce a channel. Yeah. Or they say, for example, oh, I don't want the facies yellow, which is sandstone, which is core sandstone, for example. Go to the shale without having a transition with the silt. You would like to see that geology happening, but with SIS, you cannot do that. So then what the people have done is they have implemented the trends. So now having a trend, you can control a bit better your facies distribution. In the right side, you can see an SIS realization controlling the trend, whereby, for example, you say, okay, my darker color facies, which is the shale, for example, I want them to be in the distal part of the anticline, which is more or less outside here. And in the core, I'm expecting to see more yellowish kind of sand. So therefore, I cannot go from yellow to black color without passing through orange color, for example. So using trends, if you have a trend for each of these particular facies, you can make more or less a realistic realization of your geology. But still, the transitions cannot be captured properly, right? So therefore, what the people have done, they have created what they call the truncated Gaussian simulation. And with the truncated Gaussian simulation, the main intention was try to capture the transition between the facies, which is going to give you a more realistic realization whenever you have these transitional environments. In this cartoon, you can see a picture from a short phase environment where you can have in the shallow section the upper shore phase, and in the lower section you can have the marine shales, the lower shore phase in transition. And then with truncated Gaussian simulation, you nicely can do that. You can capture the transition between those phases. In SIS, you couldn't do that before. Okay. Now, this is another example. This is in the carbonate, pinnacle carbonate, where we have used trends using TGS with trends to capture nicely the transitions, what happening between inside the reef and in the areas of away from the reef. Okay, so basically 2D trends with truncated Gaussian simulation help us to create this. There is another concept here, which is the vertical proportion curve. I don't think it's worth it to go back to statistic, but this is telling you what is the proportion, what is the volume of the faces vertically. So as you can see, what this is saying is that in the shallow section of the model, you will contain more this kind of carbonate faces, and when you go on to the deeper part of the model, you are not expecting to see that. That's kind of a trend is helping you also. We call it the vertical proportion curve. Now, with the object modeling, as I mentioned to you guys, the idea is that the user will define the objects. The user will say the dimension, the directions, the sizes, etc., the proportions, and then the software will do in an iterative manner. He will try to honor the well data first, putting these objects there. So one of the, as I mentioned before, the SIS and the TGS is a very, since they are pixel-based method, they are very fast, right? They can honor easily any amount of wells. But in object modeling, it's a bit tricky because if you have a lot of wells, a lot of data, the software will tend to take too long to finalize the realizations, right? It's an iterative process. Therefore, this method is more used when you have a less amount of data. So whenever you have a lot of data, try to put on object modeling is going to be challenging. Doesn't mean you cannot do that, but it's going to be challenging a bit. Okay. The other issue that you could eventually have is that if you are creating an object modeling, the people could start asking you, but where do you get the sinuosity of the channels? How do you know the sinuosity is that much? How do you know the width of the channels is that? How do you know the thickness of the channels could be okay, but things like that, it could be challenging. You will have a lot of parameters to be defined, and then you could end up trying to justify a lot of things there. It's possible, but again, you will need to start getting analogs and getting information from everywhere, trying to justify all the parameters that you will require to run an object model. The beauty of the method is, of course, it's going to give you a more realistic geological picture of your reservoir. Right? So now, which methods to use? How to select the method? How do we select SIS, TGS, object modeling, or MPS? So in general, if you have a transitional environment like the one that's happening, in a delta, for example, in the short phase, we tend to use more TGS, right, than SIS, for example. And whenever you have a more continental environment, like where you can see clearly define the bodies, the crevasses place, the channel, etc., you tend to use more object modeling. But at the end of the day, MPS is a method that, as I mentioned to you guys, it born like 15 or less than 20 years ago. We don't use it much. It got a potential. I've used it a couple of times, unsuccessfully, unfortunately, but it got a lot of potential, and that's something that if any one of you are doing a thesis or so, you can work in MPS to see how to implement it. There are a lot of room to improve it anyway. So at the end, the answer for which algorithm to use in your model, the answer is the best is try to combine them as much as you can. So try to make a combination between the algorithms to produce the best representation of the interpreted data, right? So then you cannot just force yourself to use only SIS because it's very easy to run. You need to ensure that you use all the tools available, all the methods available, combine them together in order to get the picture that is consistent with the data or the interpretation that we have at the moment, okay? Now, this is the time where I would like to check a bit on the bariogram and see you understood a bit of the bariogram. I think it's already 4. I don't have any issue to keep running for some time more. Are you guys okay with that?
Dania, are you guys okay with that? Dania and Siva? Can we extend the session for a while until
Probably,
Jairo?
half an hour or so.
Yeah, half an hour or more.
I think should be okay, sir.
All right. Okay. Thank you, Jairo. So I think we can proceed. Yeah.
Yeah, that's good. So let's proceed. So let's see how the bargram, going back to the bargram, and how the methods, and see if we understood a bit on my presentation. I guess it has been a bit fast, but let's try the best. Okay. So if we compare these two realizations, you could say that, what do you guys think? Which of these two realizations is having a bigger bargram range, the top or the bottom, and why? Now, this is a top view of faces. The yellow is one faces, the orange is another faces, and the gray color is another faces, right? So now you have two different top views, this one and this one. So the question is, what do you think is going to be the one that was created with the biggest range of the paragraphs, the bottom or the top?
The bottom is the bigger.
That's correct. Any reason why?
Basically, it's a little bit smoother and we can see more continuity in the sand package or yellow package as compared to the other.
Exactly. That's a good answer. Now, how about the third one? You see, is more continuous, right? So then the background range between these three is decreasing for the top one and increasing at the bottom one. So it's the range of the background is bigger, so you will have more lateral continuity, right? So more continuous, right? Now, if we look at this, now you could see that there is a direction. You can see the direction, right? Someone asks you what's happening there is because there is an isotropy, right, in that direction. So the variable range in that direction, which is, let's say, north, I don't know, probably 45 or 50 degrees east, this direction, right? This is the azimuth, and probably the length, if you take a measurement of the yellow, one of these yellow could give you a range more or less of, I don't know, let's say 2-3 kilometers, and that's what we call the major range. Now, perpendicular to that direction is what we call the minor range, right? And now, if I ask you, these realizations were created with object modeling, with sequential indicator simulation, or with truncated Gaussian simulation, or with MPS, what do you guys think? Was it object modeling? Do you think it's object modeling?
I think all are in SAS.
Yeah, that's right. Everything is SIS. As you can see, in SIS, it's pretty hard to see transition between the faces. What I mean is transition between the faces. If you look at carefully here, the yellow faces is touching the gray faces right away, right? And eventually you say the gray is shale and the yellow is sand. So you're expecting to see a transition between them. SIS is very hard to get the transitions done. Now, if we look at these other pictures, that are other realizations, they were created with DGS, which is different from SIS in the left. And the reason why is you can see how, let's say, from orange, you can go to gray, but you need to first pass by through yellow. So it's showing you a transition, right? You could say, okay, I'm expecting the high energy phases never to touch the low energy phases because by physics, doesn't make sense, right? The shells tend to be deposited in a very low energy levels and the sands could be in a higher level energy. So there would be a transition right there. So this is basically TGS. And as you can see how the bariogram can impact, right? At the top, you have a very short bariogram ranges. And here you see a very large bariogram ranges. And over here, you see a very clear anisotropy direction in the northeast, north 45 direction, okay? Now, when we look at these realizations were created with object modeling. You can see the variation between sand proportions, right? You see, there are more yellow in the bottom realization, more proportion of channels than in the top one. And you can see also sinuosity changes, right? You can see also, yeah, basically proportions, and all of them are north-south. Now, when we look at this realization, the last one, what do you guys think this realization was created with? SIS, TGS, or object modeling?
It's, I think, combination of TGS and object modeling.
That's correct. Yeah, that was a background going on with the TGS, truncated Gaussian simulation. And then on top of that, we have the object modeling, the channels running to cutting and eroding that kind of transitional background. Okay, so this is kind of a high level understanding of the how the variogram and the methods can look like in an example. Okay, and this can create yeah, go ahead.
I have a quick question, if you allow me, Dr. Haile.
Please go ahead, no problem. Fine.
Especially it's tempting because I see that it's Sipat field,
That's
right?
fine. Go ahead.
Yeah, the maps are from Sipat field. Okay, just a basic question, probably like you see the results are quite different from
Yeah.
each algorithm. Which one? I mean, in logical sense, even if we change the algorithm, the result should be something look like the same. But how come, like, I'm working on this field, so how come the results are so different, and which one you deem to be more close to the geology? Thank you.
Yeah. Okay. Yeah. First of all, this was an exercise just for you to appreciate the impact of the barograms and the algorithms, right? So now, what should be the method that you should use? First of all, you need to have a clear concept. What do you want to capture? So, and each model is different. Even though the workflow could be same, the workflow is more or less the same. You always will run the same processes and so forth. Two models are different, totally different. And what is the reason for those models to be so different? For example, the answer would be the data first, right? The data could be totally different. Or second, the interpretation of that data could be totally different, right? So you have in your team, some people believing that you have a channel system, and another people believing we have a lobes. These two modes will be totally the same. And this is real case examples. I tell you, we are working nowadays in the deep water of Sabah, and we have projects like, I don't tell you the name, but we have a project where basically initially, the initial interpretation were the turbidite system, but it was in the lobes, so a bit distal in the lobe part. So they were expecting more connectivity of the sand, right? And then we drill an appraisal well and we get a core. And once we have taken the core, we interpreted the core, and the core was a clear channel DB system. So therefore, the initial model was totally lobes, okay? It changes totally to a channel DB. Now, if you ask me which one, the answer would be depends on your data, depends on your interpretation, okay? And now, again, you could have totally different models because you have less data. Let's say your seismic not helping you at all. Let's say the seismic quality is very bad. You have a shallow gas cap that is masking all the geology in the amplitude. For example, you cannot see anything, right? So then if that's the case, you're expecting to go from one spectrum to another spectrum. But now you have a beautiful seismic with very nice quality and resolution and so that is defining you clearly the EOD, that you cannot go away from the EOD. Definitely, no matter what you do, what method you do, definitely you need to produce your seismic because your seismic is clear, right? It's showing you. Do you get that? So the answer is depends. Basically,
Yeah.
depends on the data, depends on your concept. Again.
Got it. Yeah, got it.
Okay.
So, I mean, the conceptual model matters a lot. So it should be something close to your conceptual model. Thank you.
That's correct. Yeah. Now, once you have your 3D, once you have your wells, once you have predicted your phases at your well locations, and once you have selected your concept and your algorithm to populate your phases, now you have a container full of stratigraphy and geology itself, right? Because you have the structure as well. So you have purely the geology already captured in the 3D. Now, the next step that you need to do is you cannot run volumetric with the phases only. You will need to have petrophysical properties, which are at the end, the ones that will allow you to calculate the volumes, right? So then the next step is you take the phases and you constrain your properties inside that phases to create your property model. 3D porosity, 3D permeability, 3D saturation, etc. Right? So let's talk about the property modeling then. And for talking about property modeling, we first need to understand a bit of the concept, which I guess you guys already know. What is porosity? We know the porosity is the empty space divided by the total space or total volume, right? And there are different types of porosities. We talk about effective porosity, we talk about total porosity, right? Where effective porosity is the porosity that is connected and is more linked to permeability, right? Now, permeability, you know already what is permeability. Permeability is kind of the how easy the fluid can move through the porous media, right? And permeability was first found as an adjustment. You wish adjusted constant, was a constant for, to try to link between the production of the fluid versus the pressure versus the area, right? And they found that there was a mismatch between when they were trying to develop this relationship between pressure, area, and the fluid that was flowing, right? The amount of fluid that can flow. They found out that they need kind of a constant. That's where the permeability born. And then the physical concept is saying permeability is how easy the fluid can move through the porous media. And this permeability could be effective, could be total permeability, could be also vertical permeability, horizontal permeability, relative permeability, you know. So those concepts are there. The message here is we are trying to model always the total permeability, which is linked to the porosity, okay, in the reservoir model. Now, when they talk about relative permeability, something more dynamic for the reservoir simulation. So you imagine that you have, imagine you have in a room, and in that room, if the room is full of the same kind of fluid, it's going to be easy for any particle of this fluid to move around that, right? But you have all the fluids inside the room, so then any particular fluid trying to move will find obstacles, right? And this is where the concept of relative permeability to the oil or relative permeability of the water was explained there, okay? We don't, in reservoir model, we don't use those. Those are used as an input for the dynamic simulation, which is a topic out of this presentation. The other property very important for you to know that we need to model the water saturation, or the 1 minus this guy. So 1 minus water saturation will give you the hydrocarbon saturation. So, and we need the saturation, of course, because you need to calculate how much of those pores is filled of hydrocarbon that you are calculating. And the other parameter that we explain a bit elaborate is basically the formation volumetric factor, which is coming from PVT fluid test. We take the fluids reservoir condition, you take it into the lab, and in the lab they start making experiments and start reducing the pressure and seeing how these volumes start changing with the change in pressure, and then you can estimate what could be the change in volume between extracting from the reservoir, taking this volume to surface, how much volume at the end you can sell in your time to the customers, right? Okay, so this is kind of a high level. So you will need porosity, permeability, saturation, and of course formation volumetric factor to complete your loop of your model to calculate volumes, right? This part we already explained it, why we need it. Of course, we need to calculate. Now, for porosity, or in general for property modeling, there are different algorithms, and this is a summary of deterministic algorithms. We don't use them much, to be honest. The one that sometimes we use is Kriging, okay? I've used sometimes neural nets, and these neural nets are very easy to use whenever you have a multi-attribute analysis. I used it a couple of times with multi-attribute analysis, trying to link multiple attributes extracted from the seismic to one property, let's say porosity. Then you can create the neural nets in the software, and then you can predict the porosity, okay? But this is deterministic methods. We don't apply them much. The one that we really use the most is the stochastic methods, which is basically the sequential Gaussian simulation, right? And in Petrel nowadays they improve it a bit and they call it random function, but this is basically purely sequential Gaussian simulation. And in this principle, what we are trying to do is we have noticed that there are a lot of variables, for example, porosity, that they behave in a, when you put a distribution of them, a probability density function, you would see that they behave kind of in a shape, a bell-shaped curve, right, in the normal distribution. So then, and this is not only happening in geology, happening in many other variables in the real world. So then there were some algorithms developed for trying to predict properties away from observations using this Gaussian kind of behavior. This is the one that we use for porosity. Okay, this is using, of course, you can read through, I will pass you the materials. This is using all the information, using distribution, using the well data, so it's very fast. This algorithm is a blink of an eye as well. And you can also constrain the SGS using seismic. For example, you have a cube, you could use this cube to control the porosity distribution with methods like collocated co-kriging, for example, which is also based with sequential Gaussian simulation. For permeability, the method that we use the most is basically the linear transform. And with the linear transform, what we are doing is we make a cross plot between porosity and permeability, porosity at the x-axis and permeability on the y-axis. You normally start with the core data. So the point that you see right there as the core data. And then we develop mathematical models or linear regressions to try to fit that data. And then having that linear regression, since you already have your porosity, you can calculate with the linear regression that you have found in your data, your permeability. Now, but there is a big disadvantage of this approach. And the disadvantage is, as you can see, there is a cloud. So meaning to say for one value of porosity, you have a range of outcomes of permeability, right? And then when you use a single linear transform, what you are doing is you are saying for one single value of porosity, I will always have the same output of permeability, one single value, but the data is telling me I have a range. So then there were other methods like, for example, cloud transform or collocated co-kriging, where the intention is try to capture the clouds. So it's try to capture the level of heterogeneity, you wish, for any value of porosity, because you know one value of porosity is having a range of permeability. It's not a unique value, right? So with those methods, we can estimate and we can predict these clouds that is observed at the core data. Then you have porosity. Using any method for controlling the permeability modeling with porosity, you have permeability. So, and this is controlled with phases. So porosity is being controlled to the phases. Then permeability has been controlled by porosity, therefore has been controlled by the phases, right? So everything is linked. And now this is the example of one of the example of the disadvantage of using the transform. This is what I mean. So you have one value of porosity, let's say here, and you use a single model, a linear model like this, you will have a single value of permeability always, right? But in reality, you see that there is a cloud. This is, let's say, a cloud, right? So for one value of porosity, you can have from here up to, let's say, here, a range. So this is the disadvantage of the single linear. Again, we don't do one single model. So you have, let's say, one rock type here, one rock type here, and one rock type here. You can create different models, one model here, one model here, and one model here, to try to simplify and try to capture the clouds. But the method that helps you the most is collocated co-kriging, okay? Now, having a porosity and permeability, now you can create your water saturation. In Petronas, the majority of the companies, some others, they don't use it, but in Petronas, the one that we use is saturation high based model. And the idea with the saturation high models is that we would like to reproduce the experiments that we do in the lab when we take a plaque, a piece of rock from the core, right? A plaque, we send it to the lab, and in the lab, they core a spatial core analysis. And they do experiments, and they try to predict how the capillarity due to the pore media is behaving, right? And with these capillary pressure experiments, we can estimate how much of the water can go above the contact inside the reservoir, right? Yeah. So this is what we are trying to do. So you imagine putting in a pot, for example, a lot of water, right? Put water there, and then you have straws, right? Many straws with different radius, and you put them inside the water, right? Depends on the radius of the straw, the water will start climbing up inside the straw, right? So if the radius of the straw is big, the water will go from the free water level to a height which is relatively small. But if the straw radius is smaller, so now the water, it will climb further. It's going to be higher. And at the end, you see a plot, you put many straws with different radius, and you see kind of a cross section, you can see kind of a J. So the water in the straws with big radius will climb small, and with the small radius will climb more. So you will see a J. And this is where the saturation modeling for the 3D born using the J function on the high or the high above the free water level. So for doing that, what you need a PC, which is the capillary pressure. And that capillary pressure is normally a function between the high above the free water level and the difference, the delta, between the density of the hydrocarbon and the density of the water, for example, okay? That's how we calculate the PC. This sigma cos theta is something that we estimate with a special core analysis. This is your permeability and this is your porosity. Therefore, you can calculate what we call J. This is a constant, depends on the units that you're using. If you are using feet or meters in the high. And then using that information, you plug it into the equation of the high above the free water level, and you can calculate the SW. You see that there are some constants here. This is JA and this is B. And these constants normally are associated with phases. So it depends on the phases, this A and B can have a different value. So then at the end of the day, having porosity and permeability and phases, you can use this equation to produce your water saturation. And since you have the water saturation, you can say 1 minus SW, which is the water saturation, and then you will have the amount of hydrocarbon in that particular reservoir, okay? All right, so now what we have at the end is a 3D representation of my reservoir containing geology. In the geology, you have stratigraphy, structure, right? And of course, representing the phases. Then you also will have the porosity constrained to that phases, the permeability constrained to porosity, the saturation constrained to poroperm, and also the phases. And then you're ready to go, but then you need to contact the fluid contact, right? So how we estimate the fluid contact? You have drilled wells and you already can see the contact due to the, you have well logs, right? And with the well logs, you can make certain mathematical models to calculate water saturation like Archie or Simon-Duke. So many equations are there. So you can see is at the well location, you already intersected the contact. You can interpret it right there. Then this contact is going to be used in your model to calculate volume. Now, you don't have the contact seen at the well. So what the petrophysicist normally is doing is they take the pressure from the MDT or any pressure data, and we plot the pressure versus depth. And we know the gradient of the water and we know the gradient of the hydrocarbons. And we see all those gradients inside that pressure plot. And then in the intersection between the gradient, let's say, of the oil and the intersection of the gradient with the water, in that intersection, that's where we more or less pick whatever could be a possible free water level or possible contact. And then we use those whenever we don't see at the well location, okay? So then you can calculate volume, right? But then volume will say, okay, you have one realization, so you will have one volume, right? But remember, the idea is to run multiple realizations, so then you have a set of volume to capture the uncertainty. And that's what the next topic is coming. Sensitivity and uncertainty. Again, this is the equation that we have discussed already about the volumetrics. So where is the uncertainty coming from? So the uncertainty is coming from everywhere, all the disciplines. We know that what we really know for sure is that we are uncertain when we are doing reservoir models, right? And there is uncertainty as variable as, for example, when you are picking the seismic, the way they pick, even the way they are picking the seismic, they pick up or they pick down the throw or the peak of the seismic, or they go a cycle up or down. Those kind of things are uncertain. If you put your physicists here with the same seismic, another geophysicist here with the same seismic, you ask them to interpret the two maps will have differences. They would be different, right? So we would like to capture that kind of level of differences somehow in the model. Again, even in the more precise way that you could imagine in a PVT analysis, right? We take the sample of the fluid, we send it to the lab, and even when they do the experiment of the pressure, volume, temperature, how it's changing the volume and so forth, you could see differences. There is even uncertainty at that level. So in all the disciplines, you have ranges. You don't have unique values. You have ranges, right? You have a range of porosity. You have a range of permeability, a range of saturation, and range of the contacts, even in the contacts, right? And those ranges, what we do is we take those ranges and we develop workflows. We develop workflows in the software where basically we define the ranges, change my porosity between here to here using this particular distribution, or change my map, my structure map between this map and this map. This map was created by interpreter 1, this map has been created by interpreter 2. Or change this map and this map because this map has been time to the conversion using a single function, and it has been time to the conversion using a velocity model, 3D velocity model, for example. And then there will be changes in the structure, right? Or, for example, oh, there is this fault that could be there or could not be there. So then in one model, you can put a fault, and in another model, could remove the fault, right? We can call it high confidence faults and low confidence faults, right? So we can integrate that into a single workflow, and we run all this together. Remember the variogram, for example? Picking the range of the variogram could be very uncertain because you are limited in the experimental variogram. You don't have as many points as you wish. So then it's an interpretation. So the geomodeler, it will try to fit the model variogram to the experimental variogram as much as he can, but there will be some uncertainty, right? He can make it a bit like that, a bit less. So that variation could give a bigger range, more continuous property, or smaller range, more discontinuous property. So even at the variogram level, we have uncertainty. So we put ranges. In variograms, we never put one single value of ranges. Or range. We put a range of ranges. Okay, so we put always ranges. Then putting all this together into the software, we call it a workflow, and we push the button, the software will start running. Every time he runs, he creates an equally probable realization, and then you will produce one volume. Then run another time, another volume. And at the end of the day, what you will have is a distribution of volumes. So you will have a distribution of volumes. And having that distribution of volumes, you can pick what we call, in the oil and gas industry, we use the P10 percentile, P90, and P50 percentile. So then we report, instead of one single value of volume in your field, you report a range. And then the managers, depends on the companies. There are certain companies that they are very aggressive, and even though if let's say the P90, which is the smaller volume, is not economic, they say, no, if the P50 is economic, we do the project. Some of the companies are less aggressive, more conservative, and they say, no, listen, I see the P90 is not economic, so I better don't go, right? Maybe they don't have the money to invest and they don't want to lose the money, right? Long time ago, let's say 30, 35 years ago, when we don't have that possibility of integrating everything into uncertainty and see the ranges, it was pretty difficult because they have only one model, one only chance. And the probability of that to happen, that you hit the volume with one single realization, is very, very low, the probability, right? So then there were a lot of issues in terms of economics and issues here and there like that. Now, additional to the uncertainty, there is another concept that I want you guys to have it clear, which is sensitivity. And what is the difference between uncertainty and sensitivity? In uncertainty, what you are doing is making a combination of all the properties, all the variables, with all the ranges together. So you would like to see the lows and the highs and the middles all together to see how wide could be the range of the volume, right? But in the sensitivity is different. In the sensitivity, what you are doing, let's say you have 5 parameters. Instead of combine them all, what you will do is you will fix 4 of them and keep one for you to investigate. And this one, you change it in the range that you have defined. Having this fixed, you change this. So therefore, what you will do is, let's say you change it 10 times. So you know that the effect of these 10 volumes is due to this parameter because you already fixed these guys, right? So then you see how much this guy is affecting the volume. Then you fix this guy, and then you select another one and change this one. And then do the same. Fix this guy, change the other one, and so forth. So you do that experiment in order for you to identify out of the 5, which one is the parameter which is impacting the most the volume. So let's say that the one that impacting the most the volume is the contact, the fluid contact. If you know already that is the contact, so whenever you will do a new campaign of drilling, if you wish to reduce the uncertainty in your volumetrics, you need to go and try to find the contact, because you know the contact is the one impacting the most the volume. So then whenever you drill, you say, okay, let's try to go to the flank a bit to try to see the contact. Because if you hit the contact and you know where the contact is, so before you thought your uncertainty range in volume was like this, but you know the contact is changing that drastically. So now that you know the contact, your range is smaller. so you are more accurate. Okay, that's the difference between sensitivity and uncertainty. And with that, we have done. So I have some papers here. I will keep it there for your reference. I will pass you this presentation, guys. So if you wish to go through the presentation, I'll be happy. Any questions? This is my email. So if you have any question, please send me questions there or ask me questions. This is the questions and answers part.
All right. Thank you very much, Jairo. And I think the participants are very interested on the topic. So if you have any question, please feel free to ask.
Mm-hmm.
I know we hold Jairo for a long time, but
No, that's
yeah.
no, that's good. I like it actually when the people is asking questions. Sometimes you see the presentation is prepared for 2 hours, but it's good to have questions and discussions. It's good to see.
I think Afif, would you like to ask on audio, or should I read your questions?
Okay, I can ask the question orally
Oh,
as well.
please go ahead. Yeah.
Right. Hi, doctor. So actually, I was quite interested when you explained about the facies prediction using the neural network. So I was just curious to know if there are any other methods that also use this sort of neural network for prediction or maybe automation. So I was thinking like maybe is the same kind of prediction used also for seismic volumes or to predict horizons or anything else. So maybe is there anything that Petronas is already doing that maybe you can share anything else that the innovation techniques.
Yeah, I'm not your physicist by background. We have a group in Petronas that they are developing all these algorithms, including the research group, right? They are using big data and all these things to produce. The only thing that I can tell you that I've used for facies prediction additional to neural nets is, I forgot now, fuzzy logic. If you're familiar with fuzzy logic, you would understand. You see, you look at, I was amazed to see when I started working with this fuzzy logic years ago, that I went to check one day put in the laundry, in the washing machine, my clothes and so. And I realized that in the washing machine, they say this is done with fuzzy logic. Okay, and fuzzy logic is very interesting, and it's a similar thing like neural nets, but it's a bit more how to say, interpretative, if you wish. So I've used fuzzy logic for facies modeling, and again for seismic, I know they are working. I'm not that familiar. They are working on new algorithms to make it for faster extractions and finding relationship between properties and so forth. But I'm not that familiar to that. Okay. So if you ask me which one is the method that we use the most, the people nowadays, they use the most cutoff. So they use cutoff a lot, right? And few of them they use neural nets. Nowadays, the softwares are more friendlier in that sense. You can use neural nets easily, right? And this method I told you, fuzzy logic, is not available anymore. Some theses you will see them here and there, and with Python you can program those fuzzy logic algorithms. Yeah.
I see. So for seismic related, other than like well logs, can prediction also be done using any sort of automation? Yeah.
Yeah, as I mentioned to you, yeah. For example, we had a project in Halong Bay in Vietnam, and this project is a fracture reservoir. It was discovered, and then we have used relative acoustic impedance, distance to the fault, and curvature of the structure, integrated with the neural nets to try to predict the fracture intensity in a DFN model, discrete fraction network model. So we have used it. We can use it, and it's available. In Petrel, it's straightforward to use those methods. Yeah. Okay.
How about geo bodies? Can you predict that as well?
Geobodies extraction, yeah. Again, they are using semblance and all these attributes to try to produce the geobodies. This is kind of a wish, I would say. I tell you, it's very few projects, to be honest with you. they can extract geobodies. They prefer to extract maps, but geobodies itself, the quality of the seismic is not that good, to be honest. We have done some exercises in deep water in Egypt, extracting geobodies, but in those areas, in those gas fields, it's very nice because you see the gas in the seismic is easier to extract, so we can see clearly the bodies. So we extracted those bodies. But again, if you ask me the details of the methods and the algorithm behind, I'm not at that level. This is basically your physicist level. Yeah, I've used them. I use the geobodies. I use them, but it's difficult to find people willing to extract because sometimes they feel like the quality of the seismic is not at that level to extract geobodies.
All right, Doctor. Thank you so much for answering.
Problem. Yeah.
Any other question? Okay, maybe Mr. or Miss Hayat.
Yes, sir. Sir, I have one question about the geophysics. Sir, please explain the computational geophysics, such like finite volume method, how we elaborate in the geophysics. Sir, please explain if possible.
Yeah, again, my background is geology. I have a master in petroleum engineering. So in geophysics, I'm not that familiar, to be honest. I'm more geomodeler. So I know how we use in engineering, for example, the finite methods to calculate fluid simulation, to try to see changes in saturation through time when the pressure is dropping and so forth. Or we have used these finite models to at the well level, you know, when we are trying to create nodal analysis, we use them a lot. But in seismic, I never use it. Again, I'm not the physicist, so I'm not using physics. Yeah.
Okay. Yeah. All right.
Okay,
Thank
sir,
you, Jay. Thank you. Maybe Ghazi, would you?
Thank you so much, Dr. Hale and Mr. Jayo. This lecture came as a blessing for me because I'm a reservoir model. I'm doing my PhD here, QTP. I'm not going to hold you longer. I'm not going to ask many questions at this moment. I'll be in touch on email. Just wanted to thank you so much for this presentation and hope to get in touch with you on email.
Sure, no problem. Yeah,
Thank you so much.
So no problem. Yes, yeah.
All right, thank you so much.
I'll be on holiday starting this week, and I'm planning to come back in February. So apologies if I cannot reply you before, okay? Because I'll be enjoying my already 3 years not taking holidays, so I have to take holiday now.
Yeah, COVID has done this to everyone. So anyhow, yeah, thank you so much. Whenever you feel like convenient for you, thank you.
Yeah, welcome. Thank you.
All right. Okay. Is there any other question? I think maybe we just reached to the end. And at the end, I would like to say thank you to Jairo because it was such a great contribution to the program. You almost covered the whole course learning outcomes expected. And we are really great for your contribution and happy to host your presentation. And I hope my students have learned and got ideas how you know the skill of reservoir modeling and characterization would be applicable in the industry. With that, I would like to say thank you. And I don't know if my students would like to say some words if you wish to say. If not, then we will close the session. Yeah.
Thank you. Thank you very much for the invitation and you guys to stay longer a bit. Apologize to take 40 minutes longer, but yeah,
no
thank
problem.
You
No
for
problem.
yeah, appreciate that.
Really appreciate your contribution. I hope you will continue contributing to the.
Indeed. No problem.
Yeah. Thank you very much.
Thank you.
A nice holiday. I know we took your holiday time, but thank you very much.
Thank you. Thank you. Have a good day, guys, and keep in touch. Okay.
Bye. Yeah.
Thank you. Ciao.
Yeah.
Thank you, sir.
Okay. Thank you very much for the participants. Appreciate it.
Yes, sir.
Thank you. Thank you.
Hello, sir. From where we can gain the recording?
Again,
From where we can download the recording?
I will share later on.
Sir, from where I have not registered now.
Okay. Maybe I think since you are participating from where?
Sir, I have joined from my friend ID.